In a universe brimming with mysteries, scientists estimate that there are over 100 billion planets beyond our own solar system, many of which defy our imagination. We'll uncover the strange and extreme conditions of these distant worlds, from scorching atmospheres to relentless storms. Join us today as we dive into the atmosphere and surface climates of the scariest exoplanets in our universe. When we think of planets, our minds often go to those that orbit our sun. However, exoplanets or extrasolar planets are those intriguing worlds that exist outside our solar system. The primary defining characteristic of an exoplanet is that it must orbit a star, not just any celestial body, but one that provides the necessary gravitational pull to sustain a stable path over a significant period. Another key aspect is size. Exoplanets vary immensely in size, ranging from those smaller than Earth, known as super-Earths, to gas giants far larger than Jupiter. To be classified as an exoplanet, an object must be large enough to not be a star in its own right. This means that it must not undergo nuclear fusion in its core, which is the defining trait of stars, and instead have a solid or gaseous composition that allows it to be generally classified under its own category. Additionally, exoplanets cannot be remnants of star systems, such as brown dwarfs. They must maintain their gravitational interactions that define their status as a planet. This interaction often means they are part of a more extensive system comprising other celestial bodies, which brings us to the point that many exoplanets are found in systems with multiple planets orbiting a single star. Lastly, the methods used to detect exoplanets add to their classification. Astronomers utilize several techniques, such as the transit method, where a planet moves in front of its star, causing a slight dimming that can be measured, or the radial velocity method, which observes subtle gravitational effects of a planet on its star. Together, these characteristics and detection methods enrich our understanding of planets beyond our own celestial neighborhood, expanding our cosmic horizons. As of now, astronomers have confirmed the discovery of over 5,000 exoplanets, which are planets located outside our solar system. This number continues to grow as new missions and advanced detection techniques enhance our ability to explore the cosmos. Each of these exoplanets offers a unique glimpse into the diversity of worlds that exist in our universe, varying vastly in size, composition, and distance from their parent stars. To discover these distant planets, scientists primarily employ two main methods, the transit method and the radial velocity method. The transit method involves monitoring the brightness of stars over time. When a planet passes in front of its star, it temporarily blocks a tiny fraction of the star's light, causing a measurable dimming. This approach not only reveals the existence of the planet, but can also provide insights into its size and orbit. On the other hand, the radial velocity method detects planets by observing the gravitational pull they exert on their parent stars. As a planet orbits, it causes the star to wobble slightly. This wobble can be detected through changes in the star's light spectrum, indicating that a planet is present. Together, these methods allow astronomers to paint a more complete picture of the intriguing environments that lie beyond our solar system. As technology continues to advance, we can expect even more discoveries. Next-generation telescopes and space missions are being developed to search for exoplanets, particularly those that may harbor conditions suitable for life. The ongoing quest to understand these distant worlds not only enriches our knowledge of the universe, but also inspires deeper questions about our own planet and place in the cosmos. The classification of exoplanets hinges on several key factors that define their physical and chemical properties, helping scientists distinguish between categories like gas giants, rocky planets, and ice giants. One important aspect is the planet's composition. Gas giants, for instance, are mainly composed of hydrogen and helium, making them massive but lacking a solid surface. In contrast, rocky planets have a solid terrestrial surface and are primarily made up of materials like silicates and metals. Another significant factor is the planet's size and mass. Gas giants are typically much larger and more massive than rocky planets. Their gravity is strong enough to retain thick atmospheres of gas, which can extend hundreds or even thousands of miles into space. On the other hand, rocky planets are smaller and less massive, with a structure that supports solid landforms, mountains, and valleys. This size distinction plays a crucial role in determining their evolutionary paths and potential for hosting life. Temperature also plays a critical role in classifying exoplanets. It influences the types of materials that can exist in a gaseous or solid state on a planet's surface. Ice giants, for example, are classified as such due to their unique compositions that include significant amounts of water, ammonia, and methane in the form of ice. These planets, like Uranus and Neptune in our solar system, tend to have temperatures lower than those of gas giants, which allows for the formation of volatile compounds that differentiate them from their larger counterparts. Lastly, the environment where an exoplanet resides contributes to its classification. The distance from its host star can indicate what materials could remain in solid or gaseous forms. Planets closer to a star may lose lighter elements due to their intense heat, while those in the colder regions farther out can gather ice and gases. Each of these factors intertwines to create a fascinating tapestry of planetary diversity in the universe, highlighting the complexities of planetary formation and classification. Understanding exoplanets, or planets outside our solar system, is significantly impacted by their distance from Earth. The farther away an exoplanet is, the fainter it appears, which makes observation a challenge. Telescopes must be equipped to capture light from these distant worlds, and as the distance increases, so too does the difficulty in gathering enough light to analyze the planet's atmosphere, size, and orbital characteristics. Additionally, the distance affects the methods we use to discover these planets. For instance, the transit method, which observes the dimming of a star's light as a planet passes in front, works best with nearby stars. The light from nearer stars is more intense, allowing for more precise measurements of the star's brightness changes. When we try to apply this method to distant stars, the faintness of their light can obscure these crucial signals, potentially leading to missed discoveries. Meanwhile, the radial velocity method, which measures the gravitational tug a planet exerts on its star, is also influenced by distance. Closer stars produce more noticeable shifts in their light due to the wobbling effect caused by orbiting planets. Therefore, exploring systems within a certain proximity offers a greater chance of detecting and confirming the existence of exoplanets. Ultimately, distance shapes our entire approach to studying exoplanets. It determines which stars we can realistically observe and influences our ability to study their properties in depth. To make sense of the cosmos and these intriguing worlds beyond our own, researchers continuously seek innovative techniques and more powerful telescopes, striving to bridge the gap between Earth and the outer reaches of our galaxy. Each discovery, regardless of distance, provides us with deeper insights into the nature of planets and the universe at large. Exoplanets, or planets beyond our solar system, have been discovered in numerous star systems across different constellations, each adding a unique piece to our understanding of the universe. For example, the star system known as TRAPPIST-1, located in the constellation Aquarius, is particularly significant. This system has 7 Earth-sized planets, 3 of which sit in the habitable zone, where conditions might be right for liquid water to exist. The discovery of TRAPPIST-1 has prompted astronomers to study the possibility of life beyond Earth, making it a landmark moment in astronomy. Another important system is Kepler-186, situated in the constellation Cygnus. This system is notable for harboring Kepler-186f, the first Earth-sized exoplanet discovered in the habitable zone of a Sun-like star. This finding has significant implications for the study of potentially habitable worlds and expands our understanding of the diversity of planetary systems. The existence of such planets invites questions about their atmospheres and the potential for supporting life. In addition to these, the star system LHS 1140, located in the constellation Cetus, has attracted attention due to its rocky planets. Among them, LHS 1140b is particularly interesting for atmospheric studies because it orbits a relatively nearby star, making it accessible for detailed observation. The study of these exoplanets is critical for advancing our knowledge of planetary formation and evolution, contributing to our understanding of how common or rare Earth-like conditions may be in the universe. Each of these star systems not only shines brightly in the night sky, but also serves as a portal into the ongoing quest to understand our place in the cosmos. The continued study of these exoplanets is reshaping our perspectives on astronomy and the potential for life, underscoring the importance of each discovered system and its role in the broader narrative of our universe. Space telescopes have revolutionized our understanding of the universe, especially in the realm of discovering exoplanets, which are planets located outside our solar system. Unlike ground-based telescopes, space telescopes operate above the distorting effects of Earth's atmosphere, allowing them to capture clearer images and more precise data. Their unique vantage point makes it easier to detect the faint light emitted by distant stars and to observe the minute changes when a planet passes in front of one. One of the most notable space telescopes in this field is the Kepler Space Telescope. Launched in 2009, Kepler was specifically designed to search for Earth-sized planets in the habitable zones of stars, where conditions might be right for liquid water to exist. Kepler's observations led to the confirmation of over 2,300 exoplanets, including diverse worlds like gas giants, rocky planets, and temperate zones that may harbor life. The wealth of data it provided has shaped our understanding of planetary formation and distribution throughout the galaxy. Another key player is the Transiting Exoplanet Survey Satellite, or TESS, which launched in 2018. TESS has expanded our view by surveying a wider array of stars, focusing on those that are closer to Earth. This allows astronomers to detect smaller planets orbiting stars relatively near to us, making follow-up research easier. So far, TESS has detected thousands of potential exoplanets, many of which are candidates for further study to determine their atmospheres and geological characteristics. Looking ahead, the James Webb Space Telescope, which launched in late 2021, opens even more possibilities. With its advanced instruments, Webb is capable of studying the atmospheres of exoplanets in detail. This capability allows scientists to look for the chemical signatures of life, such as water vapor, methane, and carbon dioxide, potentially bringing us closer to answering the age-old question, are we alone in the universe? Each new discovery feeds our desire to explore and understand the vast cosmos, hinting at a rich variety of worlds waiting for us to discover. Exoplanets, or planets orbiting stars outside our solar system, exhibit a fascinating variety of atmospheric conditions, each shaped by its unique characteristics and distance from its star. For instance, some exoplanets known as hot Jupiters have atmospheres filled with thick clouds, composed of sodium and potassium, due to their close proximity to their stars. These massive gas giants experience extreme temperatures, which can reach thousands of degrees. This is in stark contrast to Earth's temperate atmosphere, which supports a balanced climate conducive to life. On the other hand, some smaller rocky exoplanets like those orbiting within the habitable zone, regions where conditions can support liquid water, display a different atmospheric composition. For example, scientists have discovered exoplanets such as Proxima Centauri b, which may have an atmosphere capable of retaining heat, but could also be vulnerable to stellar winds that strip away volatile compounds. Earth, by comparison, enjoys a stable atmosphere rich in oxygen and nitrogen, elements critical for sustaining life. Further intriguing are the sub-Neptunes, which possess thicker atmospheres dominated by hydrogen and helium, creating a mini-gas giant scenario. Their upper atmospheres can be shrouded in clouds that occasionally rain down heavier elements, a phenomenon that would be unthinkable for our blue planet. Earth's atmosphere, while it does contain clouds and precipitation, maintains a clear separation of the elements needed to sustain widespread biological processes. In our exploration of these alien worlds, we uncover the incredible diversity of atmospheric phenomena. Each exoplanet teaches us about the conditions that prevail in the universe, prompting questions about the potential for life beyond our own atmosphere. As we deepen our understanding of atmospheric science in a broader cosmic context, we grow ever more curious about how life adapts to and thrives within such varying conditions. The atmosphere of an exoplanet can tell us so much about its potential to support life. Certain gases like oxygen and methane are particularly intriguing. On Earth, these gases coexist because they are produced by living organisms. When we detect them together in an atmosphere of a distant world, it raises exciting possibilities. This combination might suggest ongoing biological processes, hinting that life could be present or that its conditions might be suitable for life as we know it. On the other hand, the presence of gases like carbon dioxide, ammonia, or sulfur dioxide can signal a more hostile environment. High concentrations of these chemicals may create extreme climates or toxic conditions, making it tough for life to thrive. For instance, a thick layer of carbon dioxide can lead to a runaway greenhouse effect, similar to what we see on Venus, where temperatures soar to levels that would challenge any known form of life. Thus, while specific gases can imply potential habitability, others serve as warning signs about the harshness of a planet's environment. Additionally, understanding the balance and ratios of these gases can offer clues about a planet's geological activity and history. For example, if a planet has volcanic gases in its atmosphere, it may suggest dynamic geological processes that could recycle nutrients essential for life. Such interplay between atmosphere and geology could either sustain or negate the prospects for habitability over time. Ultimately, scientists study these atmospheric compositions meticulously. By analyzing the light spectra of exoplanets as it passes through their atmospheres, researchers gain insights into the chemical makeup of their skies. With advancements in technology, we are now more equipped than ever to unravel the mysteries of these distant worlds, moving us one step closer to understanding where life might flourish beyond our own planet. Wind patterns on exoplanets can reveal a great deal about their atmospheric conditions and potential climates. Just like Earth's weather systems, the winds on these distant worlds are influenced by a range of factors, including their temperature, surface composition, and the presence of nearby stars. By studying wind patterns, scientists can better understand how these elements interact and shape the behavior of an exoplanet's atmosphere. For instance, on a planet that resides very close to its star, we might observe super-rotating winds. This phenomenon occurs when winds flow much faster than the planet itself rotates. Such winds can create extreme temperature gradients, leading to dramatic weather events. They can also affect how heat is distributed across the planet, suggesting whether it might have zones that are hospitable or completely inhospitable to life. Additionally, the direction of winds can indicate the presence of clouds and storms. For example, strong winds might carry moisture across the surface, resulting in precipitation or cloud formations. By analyzing the data collected from observations, scientists can infer patterns of rain, seasonal changes, and even potential storms, painting a fuller picture of what the climate might be like on these exoplanets. Ultimately, understanding wind patterns is crucial for building accurate models of an exoplanet's weather system. This knowledge not only enriches our understanding of these distant worlds, but also helps us make comparisons to Earth, enhancing our grasp of atmospheric science and broadening our search for potential habitability beyond our own planet. Through the lens of wind patterns, we uncover the complexity and diversity of climates that exist in our universe. Scientists have long been fascinated by the myriad of exoplanets, which are planets located outside our solar system. The conditions on the surfaces of these distant worlds can vary dramatically based on a variety of factors, including their distance from their host stars, their atmospheres, and their compositions. For instance, a planet situated too close to a hot star might have a surface temperature that melts metal, while one far away might be perpetually frozen. Theories about these conditions are based on a combination of observational data, computer simulations, and our understanding of planetary science. One promising method scientists use to gauge surface conditions is the analysis of light from a star as it passes through a planet's atmosphere during a transit. This transit method allows researchers to discern the chemical makeup of a planet's atmosphere, revealing clues about temperature, pressure, and potential weather patterns. For example, the detection of water vapor can hint at the possibility of liquid water on the surface or even the presence of conditions suitable for life. This type of analysis has been conducted on many exoplanets, helping to refine our theories about what these worlds might be like. In addition to atmospheric studies, scientists also rely on models that simulate how different types of planets interact with their stars. These models take into account factors such as mass, size, and distance from the star, allowing researchers to predict surface conditions based on known physical principles. For instance, rocky planets are expected to have a different set of surface conditions compared to gas giants. This predictive modeling is crucial as it helps in narrowing down the search for exoplanets that may be similar to Earth. Evidence continues to accumulate as more technologies and missions are developed. Instruments such as the James Webb Space Telescope, set to observe across a variety of wavelengths, offer exquisite details of exoplanets' atmospheres and potential surface conditions. Each discovery acts like a puzzle piece, helping scientists create a more vivid picture of our universe, where the diversity of planets expands our understanding of the conditions necessary for life, both as we know it and perhaps in forms we have yet to imagine. Temperature fluctuations on exoplanets present a fascinating puzzle for scientists trying to understand planetary climates beyond our own. While our Earth has its own range of climate conditions shaped by its atmosphere and distance from the Sun, exoplanets exhibit a wide array of thermal behaviors due to their diverse environments, compositions, and orbits. These variations challenge our preconceived notions of what a planetary climate should look like and urge scientists to rethink existing climate models. For instance, some exoplanets orbit very close to their stars, resulting in extreme temperatures that can soar during the day and plummet at night. These large temperature swings can create harsh weather conditions that differ significantly from earthly experiences. Planets classified as hot Jupiters, gas giants situated near their stars, can have surface temperatures that exceed even the hottest days on Earth, leading to relentless winds and perhaps incredible cloud formations unlike anything we know. In contrast, there are exoplanets that exist in more temperate zones, where fluctuations are less extreme. Some of these distant worlds have been found to have consistent climates driven by unique atmospheric compositions that can trap heat. This opens up possibilities for stable surface conditions, resembling more Earth-like environments. However, understanding the impact of temperature variations on potential habitability becomes a delicate balancing act, as scientists consider how energy from a star interacts with a planet's atmosphere. These diverse conditions push researchers to refine their models and incorporate new variables, such as planetary rotation and the presence of specific gases. It's a dynamic area of study, one that continually reveals new insights into how planets can evolve and how their climates may become unsustainable at extreme temperatures. As we explore these alien worlds further, we are reminded of the complex dance of physics and chemistry that shapes climates across the universe, inviting us to ponder the possibilities of life in places we have yet to imagine. When we turn our attention to exoplanets, those intriguing worlds beyond our solar system, we find a variety of geological features that could reshape our understanding of what a planet can be. Scientists speculate about a range of landscapes based on the data gathered from observing these distant worlds. For instance, some exoplanets may host towering mountains, expansive plains, and deep canyons, much like those we see on Earth. Yet the processes that form these features might differ drastically due to the unique atmospheric conditions and compositions of those planets. Take the super-Earths, for example. These are rocky planets that are larger than Earth but smaller than gas giants like Neptune. Their geology may include rugged mountains formed by tectonic activity, similar to the Himalayas. However, super-Earths could also experience much more intense volcanic activity compared to our planet, leading to vast lava plains stretching across their surfaces. The heat from their greater mass and potentially more active interiors can result in landscape features that are strikingly different from what we regard as normal here on Earth. Then there are the gas giants, like the ones found in our own solar system, where the geological features are much less tangible. These planets are enveloped in thick atmospheres characterized by swirling clouds and high-speed winds, making it difficult for traditional geological processes to exist as we understand them. Instead, these worlds might host fascinating phenomena like massive storms, which could be likened to the Great Red Spot on Jupiter, a storm that has raged for hundreds of years. The presence of water, or its absence, also plays a significant role in an exoplanet's geology. Some planets might boast oceans, which can shape their surface through erosion and sediment deposition. Others may lack any liquid water entirely, leading to completely different erosive processes dominated by wind. Understanding these variations not only enriches our knowledge of planetary science, but also ignites the imagination as we ponder the diverse possibilities that await exploration in the universe. The distance of an exoplanet from its host star is a crucial factor that influences its temperature and potential for sustaining life. The closer a planet is to its star, the more intense the star's radiation it receives. This increased exposure can lead to higher surface temperatures, which might make the planet too hot for liquid water to exist, a fundamental requirement for life as we know it. For instance, many exoplanets found very near to their stars, often classified as hot Jupiters, experience scorching climates that make them inhospitable. On the other end of the spectrum, if a planet is too far from its star, it can become frigid and dark. In such cases, temperatures can drop significantly, potentially freezing any water present on the surface. This cold environment would also thwart any prospects for life. Thus, finding a balance in distance is essential. An area around a star where conditions may allow for liquid water is known as the habitable zone. Each star has its own habitable zone, which is influenced by its size and temperature. Interestingly, planets within this zone are not guaranteed to have life. The atmospheric conditions play a significant role too. For example, a planet might be in the habitable zone but possess a thin atmosphere, leading to high volatility in temperature and less likelihood of maintaining liquid water. On the flip side, a planet with a thick atmosphere could retain heat better, creating a stable environment for the possibility of life, even if it's located slightly outside the typical habitable zone. Researchers are increasingly discovering exoplanets that lie in the habitable zones of their stars. Each new find adds to our understanding of the complex interplay between a planet's distance from its star and its potential to host life. This exploration invites us to consider not just our own solar system, but the myriad worlds beyond it, each with unique circumstances that could allow life to flourish, or perhaps give rise to completely different forms of existence. The type of star a planet orbits has a profound impact on the environmental conditions present on that exoplanet. Stars vary significantly in size, temperature, brightness, and lifespan, and these factors can create vastly different climates and ecosystems. For instance, our Sun is a relatively stable, medium-sized star which has nurtured the development of life on Earth over billions of years. In comparison, larger stars burn hotter and faster, producing intense radiation that can strip away the atmospheres of nearby planets, creating inhospitable conditions. Consider red dwarfs, the most common type of star in the universe. Despite being cooler and dimmer than our Sun, these stars have incredibly long lifespans, sometimes lasting trillions of years. Exoplanets orbiting red dwarfs must be very close to their stars to maintain warmth, which often leads to a phenomenon called tidal locking. This means one side of the planet constantly faces the star while the other remains in perpetual darkness, resulting in extreme temperature differences that could challenge the existence of life as we know it. On the flip side, massive blue stars, although relatively rare, are short-lived and emit strong ultraviolet radiation. Planets situated in their habitable zone might experience harsh conditions due to stellar winds and radiation. Such environments could lead to a lack of stable atmospheres, making it difficult for life to emerge or survive. Yet because these stars burn so bright and fast, they often create heavy elements and distribute them into space, laying the groundwork for future generations of stars and planets. Such a process is critical for the overall evolution of our galaxy. Finally, how a star evolves through its life cycle also has implications for its planets. As a star ages, it changes from a stable main sequence phase into a red giant. This shift in stellar behavior can dramatically alter the conditions on the surrounding exoplanets, leading to potential habitability issues. The interplay between stars and their orbiting planets is complex and delicate, shaping not just the physical environment, but also the potential for life across the cosmos. Understanding these dynamics helps us appreciate the intricate dance of celestial bodies and the many possibilities for life beyond Earth. Tidal forces are an incredibly fascinating aspect of celestial mechanics, especially when it comes to exoplanets, those planets that exist outside our solar system. These forces arise from the gravitational pull exerted by a host star on an orbiting planet. As the planet travels in its orbit, different parts of it are attracted to the star at slightly varying strengths, leading to noticeable effects. This interaction can significantly influence how the planet rotates, often leading to a state known as tidal locking. As tidal forces act on a planet, they can cause it to deform slightly. Picture a soft rubber ball being squeezed. It changes shape, but eventually returns to its original form. However, with a massive body like a planet, these deformations can become permanent and lead to what we call synchronous rotation. This phenomenon occurs when one side of the planet consistently faces the star, creating a permanent day on that hemisphere, while the other side experiences eternal night. This is similar to how the moon is tidally locked to Earth. But the influence of tidal forces isn't limited merely to locking a planet's rotation. They also affect the length of a planet's day. Over time, as the star's gravitational pull continues to act on the planet, it can slow down the planet's rotation. Over time, as the star's gravitational pull continues to act on the planet, it can slow down the planet's rotation. This results in a gradual increase in the length of the day, as the rotational velocity adjusts to the equilibrium established by the tidal interaction. For some exoplanets, this ongoing tug-of-war can stretch across millions or even billions of years, leading to significant changes. Interestingly, the extent of these tidal effects varies based on several factors, including the distance between the planet and its star and the size and mass of the star itself. Close-in exoplanets, often found in what is known as the habitable zone, are especially susceptible to strong tidal forces, resulting in unique rotational dynamics that can shape not only their day length, but also their climate and atmosphere. This intricate dance of gravitation is a beautiful reminder of the interconnectedness of celestial bodies in the cosmos. When scientists evaluate the potential habitability of exoplanets, they consider several key factors that are crucial for supporting life as we know it. The first and foremost criterion is the location of an exoplanet within the habitable zone of its star. This zone, often referred to as the Goldilocks zone, is the region where temperatures are just right, not too hot and not too cold, for liquid water to exist on the planet's surface. Water is vital for life, making this a primary consideration. Next, scientists analyze the planet's atmosphere. A suitable atmosphere plays an essential role in sustaining life. It needs to contain the necessary gases, such as oxygen and carbon dioxide, while also providing protection from harmful radiation and maintaining suitable pressure on the planet's surface. Researchers look for indications of atmospheric composition, which may suggest the presence of life-supporting conditions. Another intriguing aspect involves the planet's size and mass. Ideally, habitable exoplanets should be rocky rather than gas giants. A terrestrial planet with a size similar to Earth helps ensure that it can maintain the right conditions for life, including gravity strong enough to retain its atmosphere. This consideration is important because smaller planets may struggle to hold on to vital atmospheric elements over time. Finally, scientists consider additional factors like geological activity, which could recycle nutrients and maintain a stable climate, and the potential presence of magnetic fields that protect a planet's surface from stellar radiation. These elements create a more comprehensive picture of an exoplanet's environment, enhancing our understanding of where life might arise beyond our own planet. Together, these criteria guide researchers in their quest to discover new worlds that could harbor the essence of life. Recent discoveries have drastically altered our views on where life might thrive beyond our solar system. For decades, scientists primarily focused on finding Earth-like planets in the so-called Goldilocks zone, an area around a star where conditions could potentially support liquid water. However, advancements in technology and exploration have opened our eyes to the possibility that life could exist in a variety of environments, not just those resembling our own planet. One profound revelation comes from the study of exoplanets, planets located outside our solar system. With powerful telescopes like the Kepler Space Telescope and Transiting Exoplanet Survey Satellite, or TESS, astronomers have identified thousands of these worlds. What's remarkable is that some of these planets are situated in extreme conditions, such as those found around red dwarf stars, which are surprisingly common in our galaxy. These stars could host multiple planets in their habitable zones, and while they emit less heat than our Sun, they might still nurture the right conditions for life. Moreover, researchers have also proposed that moons of gas giants like Europa and Enceladus in our own solar system could harbor life beneath their icy surfaces. These moons are thought to have subsurface oceans, kept warm by gravitational interactions with their parent planets. The discovery of plumes erupting from Enceladus, spewing water vapor and organic compounds into space, ignites excitement about the potential for microbial life existing in these hidden oceans. Finally, the search for life has expanded to include environments previously thought hostile, such as Venus. Recent studies have detected phosphine gas in the atmosphere of Venus, a potential indicator of biological processes. This suggests that even planets with harsh conditions might provide a safe haven for life. With each new finding, we are reminded of the vast possibilities surrounding us, igniting curiosity and hope about the existence of life in places we once overlooked. When we think about the recipe for life, it typically involves familiar ingredients like water, warmth, and a stable environment. However, scientists are now exploring the possibility that life could exist in conditions far harsher than we once imagined. Exoplanets, or planets outside our solar system, provide a fascinating setting for this inquiry. Let's delve into a few extreme scenarios where life might just find a foothold. Firstly, consider the tantalizing extremes of temperature. Many researchers have speculated that life could thrive in environments that are incredibly hot, such as those found near hydrothermal vents on the ocean floor or even on planets with scorching surfaces like Venus. Here, temperatures can reach hundreds of degrees Celsius. Some extremophiles on Earth, such as certain bacteria and archaea, have adapted to live in boiling hot springs. These organisms have evolved unique biological mechanisms to survive, suggesting life elsewhere might do the same. Then, there are the potentially frigid worlds, like distant icy moons. Take Europa, one of Jupiter's moons, which is covered in a thick layer of ice believed to insulate a vast ocean beneath. This ocean might harbor life, shielded from the intense radiation of space. In such conditions, organisms may rely not on sunlight but on chemical energy derived from interactions between water and minerals on the ocean floor, much like deep-sea vent communities on Earth. Lastly, imagine life in the harsh, acidic environments found on some exoplanets. Certain terran extremophiles thrive in highly acidic lakes and soils, showing that life can adapt to thrive even when exposed to caustic conditions. Other worlds with thick atmospheres rich in carbon dioxide and sulfuric acid could harbor similar resilient forms of life, possibly in microbial shapes, adapting to environments far removed from our earthly experiences. In the quest for life beyond Earth, it appears that the universe may stretch the definition of habitability in ways that challenge our understanding. The resilience of organisms on our own planet opens the door to the possibility that life could endure and evolve in even the most extreme environments across the cosmos. Hot Jupiters are a fascinating class of exoplanets that share some characteristics with our own Jupiter, but exist in an entirely different environment. These planets are gas giants, similar to Jupiter in size and composition, but they orbit very close to their host stars. Their proximity means that they experience extreme temperatures, often exceeding 1,000 degrees Celsius. This intense heat leads to unique atmospheric conditions that are far removed from what we see in our solar system. What makes hot Jupiters particularly interesting for scientific study is the stark contrast they present to our expectations of planet formation. Traditionally, we believed that gas giants formed far away from their stars, where it was cool enough for gases to coalesce into massive planets. However, the discovery of hot Jupiters has challenged this notion, suggesting that these planets may have migrated from colder outer regions to their current scorching orbits. This migration could offer valuable insights into planetary dynamics and the early formation of solar systems. Additionally, the atmospheres of hot Jupiters are prime candidates for study because their extreme conditions can lead to unique chemical processes. Scientists have detected elements and compounds in their atmospheres, such as water vapor, carbon monoxide, and even intriguing signs of clouds and hazes. Observing these atmospheres can help us understand not only the nature of these far-off worlds, but also the climatic processes that shape them. Lastly, the presence of hot Jupiters raises questions about the potential for life in the universe. While these planets themselves may not be habitable, they serve as valuable laboratory environments for studying atmospheric science and the potential for life-bearing conditions on other celestial bodies. As we continue to explore the cosmos, Studying hot Jupiters can reveal much about the diversity of planetary systems and the fundamental processes that govern them. Hot Jupiters are fascinating worlds that differ dramatically in temperature compared to the gas giants in our own solar system. These exoplanets, which orbit very close to their stars, experience extreme heat, with surface temperatures soaring well above those found in our solar system's outer planets. For instance, while Jupiter itself has an average temperature hovering around -200 degrees Fahrenheit, hot Jupiters can reach scorching temperatures exceeding 2000 degrees Fahrenheit. This stark difference stems from their proximity to their host stars. Hot Jupiters orbit much closer than Mercury, the closest planet to our Sun, which means they endure intense solar radiation. Their thick atmospheres, which consist mostly of hydrogen and helium, can lead to a phenomenon known as a thermal inversion, where temperatures increase with altitude instead of decreasing, creating a hot upper atmosphere. This atmospheric reaction can generate heated winds and contribute to extraordinary weather patterns unlike anything we see on gas giants in our solar system. The temperature extremes on hot Jupiters also allow for unique atmospheric chemistry. Scientists have detected the presence of exotic molecules such as sodium and potassium, which thrive under such high temperatures. This results in the possibility of bizarre cloud formations that can contain vaporized metals, pointing to conditions on these worlds that are both alien and intriguing compared to the more familiar environments on the planets we are accustomed to, such as Saturn or Uranus. The study of hot Jupiters not only expands our understanding of planetary formation and evolution, but also stretches the boundaries of what we thought was possible in planetary atmospheres. By contrast, while our solar system hosts predominantly chilly gas giants, these distant worlds challenge our imagination and offer a glimpse into the incredible diversity of planetary systems across the universe. Hot Jupiters are a fascinating class of exoplanets, large and gaseous, orbiting very close to their parent stars. Studies of these extreme worlds have revealed that they experience significant atmospheric loss due to their intense proximity to scorching stellar radiation. This process occurs through a mechanism known as atmospheric escape, where the heat from the star energizes the gases in the atmosphere, allowing some of them to reach escape velocity and dissipate into space. The implications of this atmospheric loss extend beyond just understanding hot Jupiters themselves. As scientists scrutinize these planets, they are uncovering vital information about how atmospheres behave under extreme conditions. For instance, some studies have observed that the atmospheric composition of hot Jupiters can change dramatically over time due to this loss. This finding informs our understanding of atmospheric dynamics, and it raises important questions about the potential for habitability on smaller, Earth-like planets that may be located within the same stellar systems. Moreover, these investigations highlight a critical aspect of planetary evolution. The ability of a planet to retain its atmosphere can significantly influence its future habitability. If a planet orbits close enough to its star, like a hot Jupiter, it may rapidly lose its atmosphere, leading to a barren, inhospitable environment. In contrast, a planet further from its star may retain a thick atmosphere rich in elements essential for life. Therefore, understanding these processes on hot Jupiters not only sheds light on their own fate, but also provides a framework for evaluating the habitability of other exoplanets. Ultimately, the study of hot Jupiters serves as a reminder of the diverse and dynamic nature of planetary systems in our universe. Through these investigations, scientists are piecing together the intricate puzzle of how planets form, evolve, and ultimately address the tantalizing question of what makes a world suitable for life. This pursuit enriches our knowledge and occasionally leads to unexpected revelations about the cosmos and our place within it. A super-Earth is an intriguing category of exoplanet, defined primarily by its size and mass. These planets typically weigh more than the Earth, but less than 2 to 3 times our planet's mass. This characteristic places them in a zone where gravitational forces allow for fascinating possibilities regarding their composition and environments. While many super-Earths reside within their stars' habitable zones, meaning they exist at distances where liquid water could potentially be present, their diverse characteristics set them apart significantly from our home. Unlike Earth, which is predominantly rocky, some super-Earths could be gas giants, with thick atmospheres that might envelop their solid cores. This variety in composition poses exciting questions about the potential for different geological activities and climates. Imagine planets with vast oceans, or those carpeted with certain types of metals and minerals due to the pressures they experience in their interiors. Such differences could lead to entirely new forms of geology, and perhaps even alien ecosystems. Another defining trait of many super-Earths is their varied atmospheric compositions. Some may possess swirling clouds of gases like carbon dioxide or methane, which could create extreme greenhouse effects, leading to scorching temperatures. Conversely, others might foster conditions somewhat reminiscent of Earth's, supporting liquid water and possibly life. This begs the question, what sort of life might emerge on a planet where conditions, however similar, diverge so significantly from our own? The study of super-Earths ignites our imaginations and inspires scientists on their quest to locate planets that might host life beyond our solar system. As we fine-tune our ability to discover and analyze these distant worlds, we not only expand our understanding of planet formation and evolution, but also explore the very essence of what constitutes a habitable world. The existence of super-Earths serves as a compelling reminder that our universe is filled with possibilities, and perhaps one day we could learn more about what lies beyond our familiar planet. The discovery of water or water vapor on super-Earths, planets that are larger than Earth but smaller than gas giants, carries profound implications for our understanding of the cosmos. Water is a fundamental ingredient for life as we know it, and its presence expands the possibilities of habitability beyond our own planet. Super-Earths may be rocky potential homes, harboring conditions that could support life, prompting scientists to look closer at these intriguing worlds. Understanding the conditions necessary for water to exist is crucial. On super-Earths, the pressure and temperature can vary significantly compared to Earth. Some of these planets may sit in what is known as the habitable zone, the region around a star where conditions are just right for liquid water to exist. This zone is not fixed and changes based on the type of star and the planet's atmosphere, making the study of water on super-Earths a dynamic and exciting field of research. Moreover, finding water vapor can also indicate active geological processes. The presence of water vapor might suggest that a planet has a thick atmosphere where weather systems could develop, possibly leading to surface conditions favorable for life. Such findings stimulate not just curiosity, but also the potential for future exploration. As we seek to understand our place in the universe, super-Earths with water signify that we are not alone in our quest. These discoveries could lead to identifying other life forms and deepen our grasp of planetary formation and evolution. Ultimately, the hunt for water continues to unlock doors to questions about existence, life beyond Earth, and the myriad possibilities that lie among the stars. Super-Earths, intriguing celestial bodies that lie between the sizes of Earth and Neptune, present a fascinating arena for exploring the potential for life beyond our planet. Their greater mass implies a stronger gravitational pull. This increased gravity can significantly influence not only the planet's atmosphere, but also the physical conditions on its surface, which may affect the emergence and sustenance of life. One of the primary effects of higher gravity is the retention of a thicker atmosphere. This can lead to a more stable climate, which is essential for the development of life. A robust atmosphere can help to regulate temperature and protect any potential life forms from harmful space radiation. However, maintaining such an atmosphere over time depends on the planet's geological activity and magnetic field, both of which can be influenced by its size and gravity. Yet the increased gravity presents challenges as well. Higher gravity might limit the size and mobility of organisms. Life forms might evolve to be more compact and stronger to cope with the weight of their surroundings. On a super-Earth, creatures could be built differently, perhaps resembling the dense, stocky forms of some of Earth's deep-sea organisms, rather than the elongated creatures we see on land. Overall, while higher gravity on super-Earths can enhance the possibility of a life-supporting atmosphere, it simultaneously poses unique evolutionary pressures. Thus, the potential for life on these exoplanets remains a tantalizing question as scientists continue to investigate how life might adapt to such distinct conditions. Each new discovery adds yet another layer to our understanding of what forms life could take in the cosmos. An ocean world is a term used to describe celestial bodies that possess significant amounts of liquid water, typically beneath a thick, icy crust. These worlds, found in our own solar system and beyond, are characterized primarily by their subsurface oceans, which may be warm enough to support some form of life. The presence of water, an essential ingredient for life as we know it, makes these celestial bodies tantalizing subjects of study in the search for extraterrestrial life. One of the most well-known ocean worlds in our solar system is Europa, a moon of Jupiter. Evidence for its ocean comes from several observations, including its smooth, cracked ice surface that suggests a dynamic environment underneath. Additionally, data from spacecraft like Galileo has shown strong magnetic fields around Europa, indicating that there is a massive, salty ocean beneath its icy crust, which could be up to 100 miles deep in places. Scientists believe that interactions between this ocean and Europa's rocky seabed could create chemistry similar to that found at hydrothermal vents on Earth, where life thrives in extreme conditions. Another prime candidate is Enceladus, a moon of Saturn. This small, icy body has produced dramatic geysers that shoot water vapor and ice particles into space, suggesting that a subsurface ocean is actively venting into space. The Cassini spacecraft captured images of these plumes and analyzed their composition, revealing not only water but also organic molecules, a key building block for life. This exciting discovery suggests that Enceladus may have the right conditions for microbial life to exist. More distant ocean worlds have also piqued the interest of scientists. Exoplanets like Europa-like moons or ocean planets have been identified in the habitable zone of their stars. In these distant worlds, researchers hypothesize about the existence of oceans based not only on the presence of water in their atmospheres, but also through models of their potential geology and heat sources. The exploration of these ocean worlds raises the thrilling possibility that life could exist in environments vastly different from our own, expanding our understanding of where and how life might thrive in the universe. The discovery of a subsurface ocean on an exoplanet could significantly enhance our search for extraterrestrial life. Oceans are critical habitats for life as we know it here on Earth, and they offer a stable environment where nutrients can circulate and complex chemical reactions can occur. If an exoplanet harbors such an ocean beneath its surface, it might provide the necessary conditions for life to develop, even in environments that seem inhospitable on the surface. This idea shifts our focus from planets that merely sit comfortably within their star's habitable zone, which is often defined by surface temperatures that allow water to remain liquid, to those with subsurface water. For example, the icy moons in our own solar system, like Europa and Enceladus, have sparked intrigue because their icy crusts hide vast oceans beneath, sustaining the potential for life. Exoplanets with similar characteristics could very well hold ecosystems that we have yet to imagine. Moreover, studying the chemical signatures that may come from subsurface oceans could be an indicator of life's presence. On Earth, microbial life thrives in extreme conditions, such as deep-sea hydrothermal vents and acidic hot springs. If we detect organic compounds or certain gases in the atmosphere of distant worlds, these could suggest biological processes occurring below the surface, guiding our explorations and studies toward these tantalizingly hidden realms. By expanding our criteria to include exoplanets with subsurface oceans, we widen the net for possible habitats for life beyond our own. This opens a new chapter in astrobiology, inviting a fresh perspective on where we might find life in the universe, proving that the possibilities are as vast as the cosmos itself. The discovery of exoplanets, or planets outside our solar system, with multiple oceans, raises fascinating implications for our understanding of potential life and planetary processes. Traditionally, life as we know it depends on water, making the presence of oceans an essential factor in the search for habitable worlds. When we consider exoplanets with more than one ocean, it suggests a more complex and dynamic environment, which could provide unique habitats and ecological niches. Multiple oceans on a single planet could lead to greater diversity in terms of temperature, salinity, and chemical composition. Each ocean could develop distinct ecosystems, potentially increasing the odds of life evolving in various forms. Consider how Earth hosts a range of environments from tropical seas to frigid polar waters, each nurturing different species. On a planetary scale, The interplay between these oceans could create a rich tapestry of biological and geological interactions that are not only intriguing, but vital for the potential for diverse life. Moreover, having more than one ocean could influence the planet's climate and weather patterns. Oceanic circulation plays a critical role in regulating temperature and distributing nutrients. If an exoplanet has multiple oceans, they could interact in complex ways, affecting everything from storm patterns to the availability of essential elements for life. This kind of environmental richness might support more robust ecosystems, which in turn could contribute to the stability necessary for life to thrive over extended periods. Ultimately, the implications of discovering exoplanets with multiple oceans open up intriguing possibilities in the search for extraterrestrial life. It signifies that our understanding of habitability is evolving. As we improve our techniques for discovering and studying these distant worlds, we may find that the universe holds an unexpected variety of environments, each with its potential for life, waiting to be explored. Rogue planets are fascinating celestial bodies that roam freely through the galaxy without being tethered to any star. Unlike typical exoplanets, which orbit around stars and may be tightly bound to their cosmic companions, rogue planets have either been ejected from their original systems or formed in isolation in the vastness of space. This means they glide through the dark interstellar medium, potentially without ever receiving light or warmth from a sun. One of the most intriguing characteristics of rogue planets is their mystery. Scientists estimate that there may be more rogue planets than stars in our galaxy. They can be as varied as planets are in stellar systems. Some might be similar to Jupiter, large and gas-filled, while others could be smaller, rocky bodies resembling Earth. Without the energy of a star, these planets also experience extreme cold, making their surfaces likely frigid and inhospitable. The formation of rogue planets is a topic of ongoing research. Some may arise when a planet is gravitationally flung from its original system, perhaps due to dynamical interactions or the influence of larger bodies. Others may form in isolation, in regions where materials gather and coalesce, allowing these worlds to emerge far from any stellar influence. The existence of rogue planets challenges our understanding of planetary formation and the dynamics of cosmic systems. They open up questions about how life might arise in such extreme conditions, and they invite us to imagine how many wonders might exist beyond the light of stars, drifting through the vast expanses of our universe. Rogue planets are fascinating celestial bodies that wander through space without a host star. These planets have been ejected from their original solar systems due to various gravitational interactions. What makes them particularly intriguing is the possibility that they could harbor life in environments vastly different from those on Earth. Without the heat and light of a star, rogue planets may seem inhospitable at first glance. However, some scientists suggest that these planets could still possess internal heat, generated by geothermal activity or radioactive decay. This heat can create subsurface oceans or warm atmospheres, potentially providing a nurturing ground for life. Additionally, rogue planets might have atmospheres rich in gases like hydrogen or methane, which could support chemical processes essential for life. It's important to consider that the conditions on rogue planets can vary widely. Some might be icy worlds, shrouded in frozen gases, while others could retain enough heat to allow for liquid water beneath their surfaces. The existence of such environments suggests that rogue planets could act as islands of life, even in the vast, dark expanse of interstellar space. As our technology advances, astronomers are developing better methods to detect rogue planets and study their characteristics. The understanding of these enigmatic worlds expands, and each discovery adds to the cosmic tapestry of our universe, reminding us that life may find a way to thrive in the most unexpected places. The study of rogue planets, those wandering through space without being tethered to a star, offers unique insights into the processes of planetary formation and evolution. Unlike planets that orbit stars, rogue planets were either ejected from their original solar systems or formed in isolation. This aspect makes them invaluable to scientists seeking to understand the various pathways by which planets can come into existence. By examining rogue planets, researchers can test different theories about how planets are formed in diverse environments. For instance, Rogue planets may reveal clues about the conditions present in their parent systems before their expulsion. These planets could hold remnants of their formation history, revealing the materials and processes that contributed to their development. This information could indicate the types of environments that favor the creation of planets, supporting or challenging existing models of planetary formation. Additionally, the existence of rogue planets raises intriguing questions about planetary stability and survival. The forces at play in a planet's environment can shape its evolution over time. Rogue planets often lack the warmth of a nearby star, which prompts exploration into how they maintain their atmospheres or even sustain any potential life. Understanding their characteristics allows scientists to broaden their perspective on what constitutes a habitable environment and how planets can adapt to extreme conditions. Furthermore, the discovery of rogue planets in our galaxy suggests that they might outnumber the stars themselves. This abundance challenges the traditional view of planetary systems and highlights a rich variety of planetary outcomes in the cosmos. Each rogue planet found becomes a piece of the puzzle, helping astronomers unveil the complex and dynamic history of our universe, ultimately enhancing our grasp of how planetary systems evolve throughout cosmic time. Through these wanderers, we gain a broader perspective of the universe's remarkable diversity. Technological advancements have fundamentally transformed our understanding of exoplanets, which are planets located outside our solar system. Just a few decades ago, the existence of these distant worlds was largely theoretical. Today, thanks to cutting-edge technology and innovative methods, we have confirmed thousands of exoplanets, broadening our understanding of the universe and our place within it. One of the pivotal developments in exoplanet discovery is the launch of space telescopes. Notably, the Kepler Space Telescope revolutionized this field. Operating from 2009 until its mission ended in 2018, Kepler utilized a technique called the transit method. By monitoring the brightness of stars, Kepler detected tiny dips in light that occur when a planet passes in front of its host star. This single innovation led to the discovery of over 2,500 exoplanets during its mission. Moreover, advancements in spectrometry have played a crucial role in studying the atmospheres of these far-off planets. By analyzing the light that filters through a planet's atmosphere as it transits in front of its star, scientists can determine the chemical composition of the atmosphere. This powerful method has provided key insights into the potential habitability of exoplanets, revealing the presence of elements such as water vapor, carbon dioxide, and even methane. In recent years, ground-based observatories have also embraced new techniques and larger telescopes equipped with advanced adaptive optics. This technology corrects the blurring effects of Earth's atmosphere, enabling astronomers to observe exoplanets more clearly. With these combined advancements in space and ground-based technologies, our ability to discover and study exoplanets continues to expand, uncovering new worlds and exciting possibilities for life beyond Earth. Artificial intelligence plays a transformative role in the study of exoplanets, the intriguing worlds orbiting stars beyond our solar system. With the sheer volume of data generated by telescopes and space missions, traditional methods of analysis often fall short. Artificial intelligence can sift through vast amounts of information quickly and efficiently, identifying patterns that human scientists might miss. This capability is particularly crucial when detecting tiny changes in star brightness that may indicate an exoplanet is passing in front of a star, a method known as the transit method. One way AI contributes is through the development of machine learning algorithms. These algorithms can be trained using data from known exoplanets, allowing them to recognize the unique signatures associated with planetary transits. By doing so, AI can help categorize and prioritize potential exoplanet candidates for further study, significantly speeding up the research process. The accuracy of these algorithms has improved so much that they can sometimes even uncover new planets in historical data sets that scientists had previously overlooked. Furthermore, AI is utilized in analyzing the atmospheric composition of exoplanets. By examining the light that passes through a planet's atmosphere during transits, researchers can gather clues about the elements present. Here, machine learning aids in interpreting this spectral data, identifying the chemical signatures that indicate the presence of gases such as water, carbon dioxide, or methane. This information is vital for assessing whether an exoplanet might be habitable or even host life. The integration of artificial intelligence into exoplanet research enhances our ability to process and analyze massive datasets, revealing new worlds and deepening our understanding of their characteristics. As these technologies continue to evolve, they promise to revolutionize our approach to finding and studying exoplanets, bringing us closer to answering the profound question of whether we are alone in the universe. The James Webb Space Telescope, often referred to simply as Webb, is poised to revolutionize our understanding of distant planets in ways that previous telescopes simply could not achieve. One of the remarkable features of Webb is its ability to observe the universe in infrared light. This capability allows the telescope to peer through cosmic dust and gas, which often shroud celestial objects from view. By capturing this infrared light, Webb can uncover the hidden details of distant star systems and explore the atmospheres of exoplanets, which are planets located outside of our solar system. What sets Webb apart is its unprecedented sensitivity and resolution. With its powerful instruments, it can detect the faint light from afar, enabling astronomers to study the chemical compositions of exoplanet atmospheres in detail. This insight is crucial, as understanding what these atmospheres are made of can give us clues about their potential habitability. For instance, the presence of certain gases might suggest biological processes similar to those found here on Earth, igniting our imaginations about life beyond our planet. Additionally, Webb is designed to focus on some of the most intriguing planetary systems, particularly those that resemble our own. This includes studying various stages of star and planet formation, as well as observing the evolution of planetary systems. Each observation delivered by Webb has the potential to refine our models of how planets form and develop over time, enhancing our grasp of the cosmos. The introduction of the James Webb Space Telescope represents a significant leap forward in our scientific toolkit. By revealing the atmospheric secrets of distant worlds and examining their formation and evolution closely, Webb not only enhances our understanding of these far-off planets, but also offers a broader perspective on the universe's diversity. Each discovery opens up new questions, fueling a cycle of curiosity and exploration that may reshape our view of life in the cosmos. The discovery of exoplanets has profoundly reshaped our understanding of humanity's place in the universe. Until a few decades ago, our solar system was thought to be unique, a solitary oasis of planets circling a singular star. However, astronomers have now identified thousands of exoplanets, planets orbiting stars outside our solar system. This realization has expanded our view, indicating that the universe is teeming with countless planetary systems, each possibly hosting conditions conducive to life. With over 5,000 exoplanets confirmed, our perspective shifts not just in terms of numbers, but in the diversity of these worlds. Some orbit close to their stars in scorching heat, while others lurk in the frigid reaches of space. Many lie within a star's habitable zone, where conditions might be right for liquid water, a crucial ingredient for life as we know it. These discoveries suggest that the ingredients for life may be more widespread than we previously imagined, fueling the hope that we might someday find extraterrestrial life. Moreover, the nature of these planets challenges our definitions of habitability. Some exoplanets exhibit atmospheres unlike anything on Earth, with clouds of vapor and gases that could sustain alien ecosystems. The variety of conditions observed across different exoplanets invites us to reconsider our understanding of what life can be and where it can thrive. This opens the door to the exciting possibility that life exists in forms beyond our comprehension. Ultimately, the search for exoplanets has ignited a sense of wonder about our cosmic environment. Humanity is no longer isolated in a vast, empty cosmos. Instead, we belong to a vibrant universe filled with potential neighbors, each one with a unique story and possibilities yet to be discovered. This realization encourages both humility and optimism as we reflect on our existence and the future of exploration in the cosmos. Throughout history, humanity has had a deep fascination with the stars, leading to the creation of various stories and myths that explore the possibility of life beyond our own planet. Across cultures, These tales reflect our curiosity and hope, weaving together elements of the cosmic with the possible existence of extraterrestrial beings. In ancient Mesopotamia, for example, the Sumerians believed in a pantheon of gods who came from the heavens. The Anunnaki were alleged to have descended from the stars to shape humanity and impart knowledge. This narrative not only illustrates an early connection between deities and the cosmos, but also plants the seeds for concepts that resemble the search for life on other worlds, as if granting the idea of celestial visitors a sacred status. Moving to the Americas, many indigenous cultures have their own interpretations of the stars and potential inhabitants. The Hopi tribe, for example, speaks of the Kachinas, spiritual beings who inhabit the stars and bring life to the earth. Their stories often intertwine themes of balance and harmony, suggesting that life exists in the cosmos and is inherently connected to life on Earth. Such narratives encourage a respectful view of the universe and the life forms it may harbor. As technology advanced and space exploration became a reality, these myths transformed into poignant inquiries about extraterrestrial life. The modern fascination with UFOs and the search for intelligent civilizations, such as signals from distant planets, echoes ancient stories while relying on scientific inquiry. Today, we continue to seek answers that our ancestors only speculated upon, reminding us that the quest for knowledge is a timeless journey that transcends cultures and epochs. The discovery of exoplanets, which are planets orbiting stars outside our solar system, has captured the imagination of the public and scientists alike. These findings spark curiosity about the potential for life beyond Earth and challenge our understanding of the universe. As new techniques and technologies emerge, such as powerful space telescopes and advanced imaging methods, researchers continue to find new worlds, adding to an ever-growing catalogue. This excitement not only fuels public interest, but also ignites discussions about our place in the cosmos. As interest in exoplanets grows, so does the support for astronomical research. Governments and private organizations recognize the value of these discoveries, which have profound implications for science and humanity. Funding for astronomy projects tends to increase when there's public enthusiasm. People are inspired by the idea of finding Earth-like planets where life might exist. This excitement often translates into higher budgets for space missions and supporting technologies, which further enhance our ability to explore the universe. Moreover, exoplanet discoveries serve as a gateway to broader conversations about science and technology among the general public. Documentaries, articles, and social media have helped disseminate fascinating stories of distant worlds, fostering a collective sense of wonder. Events like the discovery of water on exoplanets or the detection of potential biosignatures generate significant buzz, encouraging educational initiatives and science outreach programs. This cultural shift towards valuing scientific inquiry ensures that more people are engaged and invested in astronomical research. In this burgeoning arena, collaborations between universities, space agencies, and commercial enterprises become increasingly common. As public interest swells, so does the appetite for funding innovative research that could lead to groundbreaking discoveries. The more we learn about exoplanets, the more we also learn about the universe and our own planet, fueling an enduring cycle of curiosity, investment, and discovery in astronomy. As we venture deeper into the cosmos, several upcoming missions and technologies are set to enhance our understanding of exoplanets significantly. One of the most anticipated is the James Webb Space Telescope, launched in December 2021. This powerful instrument will allow astronomers to observe exoplanets in unprecedented detail, particularly focusing on their atmospheres. By analyzing the light that filters through an exoplanet's atmosphere during transits, scientists can detect the presence of important molecules, such as water vapor, carbon dioxide, and potentially even signs of life. Beyond the Webb telescope, the European Space Agency is preparing the Ariel spacecraft, scheduled for launch in 2029. Ariel's mission will be to survey a large number of known exoplanets, focusing on their compositions and atmospheric conditions. By studying over 1,000 exoplanets, this mission aims to provide comprehensive insights into how these distant worlds form and evolve. This extensive data could reveal patterns that help us understand the diversity of planetary systems and the conditions that may give rise to life. Furthermore, ground-based telescopes are also advancing. The extremely large telescope, currently under construction in the Chilean Andes, will feature a mirror 39 meters in diameter. This remarkable instrument will significantly enhance our ability to directly image exoplanets and analyze their atmospheres. By combining the power of this telescope with advanced techniques like adaptive optics, scientists anticipate being able to observe planetary details that were once thought impossible. In addition to these specific missions, numerous smaller projects and innovative technologies are emerging. The use of artificial intelligence to analyze vast amounts of data from exoplanet surveys is revolutionizing the field. This technology can identify patterns and signals in complex datasets, making it easier to locate promising candidates for further study. With these advancements on the horizon, our exploration of exoplanets is set to reach new heights, expanding our understanding of the universe and perhaps even uncovering more about our own origins within it. Astronomers are constantly seeking new techniques to enhance the detection of smaller, Earth-like exoplanets. One of the primary methods is the transit method, where scientists monitor the brightness of stars for periodic dips in light. These dips are created when a planet transits or passes in front of its host star, blocking a portion of its light. To improve this method, astronomers are using more powerful space-based telescopes that can minimize the interference of Earth's atmosphere and detect even fainter signals from distant stars. Another significant development in the quest for Earth-like planets is the use of advanced imaging techniques. Telescopes equipped with specialized coronagraphs can block out the intense light from stars, allowing astronomers to see the much fainter planets that orbit them. This technology, combined with adaptive optics, sharpens images by compensating for atmospheric distortions. This dual approach helps researchers capture clearer pictures of planets that are similar in size and composition to Earth, even in star-rich regions of the sky. Moreover, astronomers are leveraging the power of data analysis and artificial intelligence. By using machine learning algorithms, they can sift through vast amounts of data collected from missions like the Kepler Space Telescope and the Transiting Exoplanet Survey satellite. These algorithms can quickly identify potential exoplanet candidates that might have been overlooked by traditional methods, thus increasing the chances of discovering Earth-like worlds. Finally, the launch of future space missions, such as the James Webb Space Telescope and the upcoming Habitable Worlds Observatory, aims to revolutionize our understanding of exoplanets. These telescopes are designed to analyze the atmospheres of discovered planets, looking for key indicators of habitability, like water vapor or signs of chemical processes that could suggest the presence of life. Together, these advancements arm astronomers with powerful new tools to explore the vast cosmos in their relentless quest for Earth-like exoplanets. As we stand on the threshold of exploring and potentially colonizing exoplanets, we encounter a host of ethical considerations that demand our attention. First and foremost, there is the question of stewardship. If we discover life, even in its simplest forms, on these distant worlds, we must ask ourselves, are we prepared to protect and preserve these ecosystems? Introducing Earth-based organisms could disrupt these alien environments in ways we cannot predict, leading to irreversible damage. Moreover, there are ethical concerns about ownership and exploitation. Just as the exploration of our own oceans and lands has led to conflicts over resources and rights, the prospect of claiming exoplanets raises similar dilemmas. Who has the right to settle on or utilize resources from these planets? Should it be treated as a shared human heritage, or should certain nations lead the appropriation ship? These discussions will shape our approach to interstellar exploration and reflect our values as a society. Another key consideration is the technological impact on our society. The rush to colonize could lead to environmental neglect back on Earth. As we prioritize investment in space, we must also ensure that pressing issues at home, such as climate change and social inequalities, do not fall by the wayside. The technological advances promised by space exploration could foster incredible progress, but they also risk diverting attention and resources from urgent global needs. Finally, we must contemplate the long-term implications of colonization. Settling other planets could carry profound consequences for our identity as Earthlings. How do we define humanity when we begin to create outposts beyond our home? In this grand adventure into the cosmos, we should embrace our responsibility to cultivate a future that prioritizes ethical exploration and the well-being of all life, both on Earth and beyond. Each question we ponder about exoplanets serves as a reflection of who we are and how we wish to relate to the universe. Exoplanets, or planets that orbit stars outside our solar system, are reshaping our understanding of life's origins and the biological processes that sustain it. As astronomers discover thousands of these distant worlds, they are beginning to unveil how conditions on these planets might encourage or hinder the emergence of life. The variety of environments on exoplanets expands our definition of habitability, proving that life could potentially thrive in places we once considered unfriendly. Many of the discovered exoplanets are in what scientists call the habitable zone, which is the range of distances from a star where liquid water can exist. Water is vital because it acts as a solvent for biochemical reactions. By studying these exoplanets, researchers can explore not only the presence of water, but also other essential elements for life, such as carbon and nitrogen. Understanding the components and conditions under which life could emerge on different worlds helps scientists piece together how life on Earth may have originated. Moreover, the atmospheric composition of these exoplanets plays a crucial role in informing us about biological processes. Astronomers analyze the light from stars that filters through a planet's atmosphere to identify gases like oxygen, methane, and carbon dioxide. The presence of certain gases ignites intrigue because they can indicate biological activity. For instance, methane could imply that something is actively producing it, as on Earth, where it is often produced by living organisms. Studying exoplanets not only informs us about the potential for extraterrestrial life, but also prompts a deeper understanding of the complex processes that sustain life here on Earth. It encourages us to appreciate the delicate balance of conditions required for life, and it suggests that while life may be rare, it could also be resilient, finding a way to thrive in diverse environments throughout the cosmos. Gravity is a fundamental force that plays a significant role in shaping not just the physical characteristics of an exoplanet, but also the potential life forms that might inhabit it. Each planet's unique gravitational pull influences everything from the structural makeup of creatures to their mobility and even their reproductive strategies. On planets with stronger gravity, life forms may develop denser and sturdier bodies to support the increased weight. The extra gravitational force could lead to shorter, stockier organisms, akin to how some animals on Earth, like frogs, evolve in denser environments. Conversely, on planets where gravity is weaker than Earth's, we might expect to see more elongated or lighter forms of life. Creatures might evolve longer limbs or wings, giving them an advantage in navigating their environment without being weighed down. This could lead to fascinating possibilities, such as flying organisms that can glide effortlessly through the air, or even animals that explore vast distances without tiring easily. Moreover, a planet's gravity can impact an atmosphere's ability to retain gases and support water cycles. In a low-gravity setting, it might be more challenging for a planet to maintain a thick atmosphere, which is crucial for mediating temperatures and providing the necessary elements for life as we know it. Alternatively, a planet with high gravity might hold onto a denser atmosphere, allowing for diverse ecosystems suited to the conditions present. Finally, the impact of gravity extends to the planetary environment itself. For instance, it can influence weather patterns, surface liquid movement, and geological activity, all of which can create various niches for life forms. Understanding these dynamics opens up our imaginations to the diverse possibilities for life on exoplanets, encouraging scientists to explore these distant worlds with renewed curiosity and excitement. Astrobiology, the study of life in the universe, plays a crucial role in helping us understand where life might develop beyond our planet. At its core, this field combines insights from biology, chemistry, geology, and astronomy to create a comprehensive picture of what conditions are necessary for life to thrive. By examining life as we know it on Earth, astrobiologists can identify the fundamental characteristics and environments that support living organisms. One of the key areas astrobiology explores is the search for extremophiles, organisms that can survive in extreme conditions. These remarkable life forms exist in some of Earth's most inhospitable environments, including hot springs, deep ocean vents, and the icy landscapes of Antarctica. This discovery expands our understanding of potential habitats beyond Earth. For instance, Moons like Europa, with its subsurface ocean, or Enceladus, spewing plumes of water vapor, might be more promising for life than we once thought. Astrobiologists also focus on identifying biosignatures, which are indicators of life that we could detect in other planets' atmospheres. For example, the presence of certain gases like oxygen or methane might suggest biological activity. As we develop new technologies and telescopes, the ability to analyze the atmospheres of exoplanets, planets orbiting other stars, becomes increasingly achievable. By gathering data about their compositions, we can refine our predictions about which worlds might harbor life. Ultimately, astrobiology guides our exploration, informing where we should direct our search for extraterrestrial life. By understanding the conditions that sustain life on Earth and identifying potentially habitable environments in the cosmos, we stand at the threshold of extraordinary discoveries about life beyond our own planet. The ongoing research not only ignites our imagination, but may soon provide answers to one of humanity's oldest questions. Are we alone in the universe? When scientists search for exoplanets worthy of exploration, they consider several key characteristics that make these distant worlds compelling. One of the foremost criteria is the planet's location within the habitable zone, often referred to as the Goldilocks zone. This is the region around a star where conditions may be just right for liquid water to exist. Water is essential for life as we know it, making these planets prime candidates for further study. The composition of the planet also plays a vital role in determining its probability to support life. Rocky planets like Earth and Mars are of particular interest because they offer solid surfaces and atmospheres that may be hospitable to living organisms. In contrast, gas giants, while fascinating, are less likely to be suitable for exploration as they lack solid ground and have extreme atmospheric conditions that could be hostile to human life. Furthermore, the presence of an atmosphere can significantly enhance a planet's potential for exploration. An atmosphere might provide protection from space radiation, regulate temperature, and even contribute the necessary elements for life. Scientists analyze atmospheric composition through techniques like spectroscopy, which analyzes the light from the planet's star as it passes through the atmosphere. This helps detect gases that may indicate biological processes, such as oxygen or methane. Lastly, proximity to Earth is a crucial factor. Planets that are closer, such as those found in the nearest stars, allow for the possibility of future exploration missions with existing technology. The combination of being in a habitable zone, having a rocky composition, possessing a suitable atmosphere, and being relatively nearby makes certain exoplanets the most exciting targets for human exploration, fueling our fascination with the cosmos and the possibilities that lie beyond our own planet. The quest to sustain human life on exoplanets, distant worlds beyond our solar system, begins with understanding the features that make these celestial bodies potential homes. Scientists focus on identifying exoplanets situated within what is termed the habitable zone, an area around a star where conditions may be just right for liquid water to exist. Liquid water is essential for life as we know it. By analyzing data collected from telescopes and space missions, researchers narrow down a list of candidates that could support life. Once we find an exoplanet that meets these initial criteria, the next step involves assessing its atmosphere and surface conditions. This requires advanced technology, as most exoplanets are light years away. Telescope missions like the James Webb Space Telescope aim to decipher the atmospheric composition of these distant worlds. Detecting elements like oxygen or methane can signal biological processes, hinting that these planets might support life, a crucial factor for human sustenance. If we contemplate the actual colonization of an exoplanet, we must also consider the challenges of space travel. The vast distances involved mean that any mission would take many years, perhaps decades. This leads scientists to explore concepts of advanced spacecraft capable of traveling at a significant fraction of the speed of light. Innovations in propulsion technology and life support systems are vital if we are to transport humans to these far-off places and enable them to survive long-term. Finally, should we reach an exoplanet, methods for creating sustainable living environments would be paramount. This could involve using local materials to build habitats, developing agriculture suited for the alien surroundings, or even terraforming, a process of modifying the planet's environment to make it more Earth-like. Each of these steps requires careful planning and creativity, ultimately revealing the incredible potential for humanity's future among the stars. Transporting humans to an exoplanet presents an array of challenges that reflect the complexities of space travel itself. First and foremost is the sheer distance involved. Exoplanets, meaning planets outside our solar system, can be light years away, which poses a significant hurdle in terms of travel time. Even with our fastest spacecraft, it could take years, possibly even centuries, to reach these distant worlds. So, one critical consideration is developing propulsion systems that can achieve much higher speeds than what we currently possess. Another key challenge is ensuring the safety and well-being of the astronauts during the long journey. This includes providing life support systems that can sustain humans for extended periods. Astronauts will need a reliable supply of air, food, and water, all while also maintaining physical and mental health in a confined space. Creating a self-sufficient habitat that recycles resources efficiently would be vital. Moreover, the psychological aspects of isolation and confinement need to be addressed, necessitating support systems that maintain morale over long stretches of time. Radiation exposure in space represents a substantial risk as well. Outside the protective shield of Earth's atmosphere, astronauts are exposed to harmful cosmic radiation, which can increase their risk of developing cancer and other serious health issues. To mitigate this, spacecraft might need to be equipped with advanced shielding materials or utilize the structure of the ship itself in innovative ways to create safe zones. Lastly, there are the questions of how to land on and explore an exoplanet's surface, assuming we find one that is potentially habitable. Exoplanetary climates can vary dramatically from those on Earth, influenced by several key factors. One of the most significant aspects is the distance from their host stars. The location of an exoplanet within the so-called habitable zone can determine whether it possesses liquid water, a crucial ingredient for life as we know it. If a planet orbits too closely, temperatures may soar, leading to a scorching, inhospitable atmosphere, while those orbiting too far could turn into icy worlds, devoid of warmth and liquid water. Another important factor is the composition of an exoplanet's atmosphere. Some exoplanets have thick atmospheres, composed of gases like carbon dioxide, which can create a greenhouse effect, trapping heat and resulting in much higher surface temperatures. For instance, the famous exoplanet known as WASP 121b has a gaseous envelope so dense that it can create extreme weather patterns, including clouds that may rain molten metal. Such conditions starkly contrast our more temperate, balanced Earth atmosphere, which consists of nitrogen and oxygen. Surface conditions on exoplanets can also be influenced by their geological activity. Some planets show signs of active volcanism, which can release gases and materials into their atmosphere, thus shaping their climate over time. Other exoplanets may have no tectonic movement, resulting in static climates where temperatures and weather patterns remain fixed. It's fascinating to consider how geological processes on these distant worlds shape their environments, similar yet different from our own. Moreover, an exoplanet's size and density play crucial roles in determining its climate. Larger planets can hold onto thicker atmospheres and have stronger gravitational pulls, affecting how heat is retained. On the other hand, smaller planets might struggle to maintain a stable atmosphere, resulting in exposed surfaces that are highly sensitive to temperature fluctuations. As scientists continue to discover and study these diverse climates, they deepen our understanding of how life might exist beyond Earth, showcasing the multitude of environmental conditions that could host life in our universe. Seasonal changes on exoplanets can have profound effects on their ecosystems, much like the seasonal shifts we experience on Earth. These variations often stem from a planet's axial tilt, orbital eccentricities, and distance from its star. When a planet experiences seasons, it can create dramatic fluctuations in temperature, light, and precipitation. These changes can dictate the types of life that can thrive in specific regions, influencing their development, behavior, and reproductive cycles. For instance, on a planet that tilts significantly like Earth, summers may bring lush plant growth, while winters could challenge the survival of many species. Plants may adapt to flourish during warmer months and enter a dormant phase when conditions are harsh. Creatures relying on these plants for food must also adapt, potentially altering their diets or migration patterns to align with the seasonal availability of resources. This synergy between plants and animals can elevate the complexity of the ecosystem, fostering a rich web of interactions. On exoplanets with more extreme seasonal variations, the impacts could be even more fascinating. For example, consider a world with an elongated orbit. During its closest approach to its star, heat and light might saturate the surface, triggering massive blooms of life. In contrast, when farther out, frigid conditions might lead to widespread dormancy. This cycle could foster unique survival strategies in life forms, from those that develop quick growth cycles to others that can endure prolonged periods of harsh conditions. Moreover, the possibility of different atmospheres and chemical compositions on exoplanets can profoundly influence how seasons affect ecosystems. A world with a thick atmosphere and substantial greenhouse gases might see less extreme temperature changes, supporting more stable ecosystems year-round. Conversely, a thin atmosphere might lead to rapid temperature swings, forcing life to evolve remarkable adaptability. Understanding these dynamics on exoplanets opens up endless possibilities in our quest to discover life beyond our own planet, reminding us just how interconnected climates and ecosystems can be. The study of exoplanets, worlds that orbit stars beyond our solar system, presents a fascinating challenge to our understanding of weather phenomena. Earth-based meteorological models, which have been honed over decades of observation, are tailored to our unique atmospheric and climate conditions. However, exoplanets may have vastly different environments, including exotic atmospheres, unusual compositions, and extreme temperatures, leading to weather patterns that defy our current models. For instance, some exoplanets experience temperatures that can reach thousands of degrees, potentially causing heavy metal clouds, something we simply do not encounter on Earth. One intriguing aspect is the discovery of tidally locked exoplanets. These are worlds where one side constantly faces their star, while the other remains in perpetual darkness. This stark temperature difference can create intense wind patterns and localized climate systems that boggle the mind. Our current models, which often assume a more uniform atmospheric temperature, struggle to accurately predict the dynamics of such extreme weather systems. These planets might also experience peculiar storms or even entirely new types of precipitation, challenging everything we think we know about meteorology. Additionally, some exoplanets exhibit atmospheres rich in gases that don't exist within our own. For example, these atmospheres can contain compounds like hydrogen, helium, and various acidic or metallic vapors. As we attempt to create models to predict weather on these distant worlds, we need to factor in the chemical interactions that can lead to weather phenomena entirely alien to us, such as clouds formed from vaporized metals. The exploration of these diverse weather systems signals exciting new frontiers for meteorological science. As we refine our understanding and gather more data from powerful telescopes and future missions, we will continually adapt our models. This not only enriches the field of comparative meteorology, but raises profound questions about the universality of weather systems throughout the universe, driving us to rethink what we know about atmospheres far beyond our blue planet. The transit method is one of the most effective techniques astronomers use to discover distant exoplanets. Essentially, this method observes the slight dimming of a star's light, which occurs when a planet passes in front of it from our perspective on Earth. This event is known as a transit. Though it might seem like a simple idea, the subtleties of detection require a sophisticated approach. One of the key techniques involves monitoring the brightness of stars over time. Astronomers collect data continuously, creating a light curve that tracks variations in brightness. When a planet transits, it causes a small but noticeable decrease in the star's brightness. By analyzing the depth and duration of this dip, scientists can infer important details about the planet, such as its size and orbit. For instance, a larger planet blocking more light will create a more significant drop in brightness compared to a smaller one. Moreover, researchers utilize precise photometry, which means measuring the intensity of light very accurately. This level of precision is essential because the changes in brightness caused by a transit are typically quite small, around 1% or even less for distant stars. Utilizing advanced telescopes equipped with sensitive instruments, astronomers can detect these subtle changes amidst the stellar noise. This is why space telescopes like Kepler and TESS have been pivotal. They can observe many stars simultaneously, increasing the chances of spotting transiting exoplanets. Additionally, follow-up observations play a crucial role. After detecting a potential transit, astronomers may conduct further observations to confirm the existence of the planet and gather more data. This can include looking for additional transits to confirm a planet's orbital period, or using other techniques, such as radial velocity measurements, to study the planet's mass. Each of these steps builds a clearer picture of the exoplanetary system, enhancing our understanding of the diverse worlds that exist beyond our own solar system. The radial velocity method has been a pivotal tool in uncovering the secrets of exoplanets, particularly in determining their masses. This technique relies on the principle of Doppler shift, which changes the frequency of light based on the motion of an object. As a star wobbles slightly due to the gravitational pull of an orbiting planet, its light spectrum shifts. By measuring these shifts, astronomers can infer both the presence of the planet and its mass. When a planet orbits a star, it not only affects the path of the star, but causes a subtle movement towards and away from us. This movement leads to small but measurable changes in the star's velocity, which can be detected by examining the light it emits. The more massive the planet, the greater the gravitational pull it exerts on the star, resulting in a more pronounced radial velocity signal. Consequently, scientists gain insights into the planet's mass, even if the planet itself cannot be seen directly. This method has transformed our understanding of exoplanet diversity. Early on, astronomers found that many of the first discovered exoplanets were surprisingly massive, often resembling gaseous giants much like Jupiter. However, continued advances in this field have enabled researchers to detect smaller planets as well, allowing us to understand a spectrum of planetary masses, including the elusive rocky planets that might harbor life. Ultimately, radial velocity measurement not only provides accurate masses for these distant worlds, but also sheds light on how they might form and evolve. As we piece together the dynamics of star-planet interactions, we gain a more robust picture of the myriad of planetary systems in our galaxy, enriching our quest to understand our place in the cosmos. Detecting the atmospheres of distant exoplanets is an exciting area of research that expands our understanding of the universe. However, the methods currently employed come with significant limitations. One of the primary techniques used is called transmission spectroscopy, which relies on observing the starlight that passes through a planet's atmosphere during a transit. Unfortunately, this technique is most effective for larger planets that block substantial amounts of light and for systems with bright nearby stars. As a result, many smaller, potentially habitable worlds remain elusive, hidden behind the glare of their parent stars. Another challenge is the atmospheric composition itself. Exoplanets can have atmospheres that are thin or consist of gases that are difficult to detect. Additionally, many atmospheres can be obscured by clouds or hazes, complicating the interpretation of data. In many cases, the signals we receive from these distant atmospheres are incredibly faint, often buried beneath the noise of the star's light. This means that even when scientists manage to collect useful data, distinguishing the specific components of a planet's atmosphere requires sophisticated models and sometimes even a bit of guesswork. Moreover, our current telescopes and instruments have limitations in their resolution and sensitivity. While advancements are being made, such as the launch of space telescopes designed with specialized capabilities, the technology is still catching up to our ambitions. Telescopes located on Earth, for instance, are hindered by atmospheric distortions, which can blur the signals we receive from space. Observing from the ground means dealing with weather conditions and pollution, both of which can affect the accuracy of our findings. Lastly, the sheer distances involved create a time lag in our discovery process. The light we see from distant planets can take years to reach us, meaning that while we might identify an exoplanet today, we are observing it as it was long ago. As our techniques and technologies evolve, the challenge remains not just to detect an atmosphere, but to understand the complex interplay of its components. Despite these hurdles, the search for exoplanet atmospheres continues to be a promising and profoundly inspiring venture into the cosmos, one that may very well lead to extraordinary discoveries about our place in the galaxy. Astronomers have developed a structured system to categorize and name new exoplanets, those fascinating worlds outside our solar system. This process begins with identifying the exoplanet's characteristics, including its size, mass, and the nature of its orbit around its host star. Such details help scientists position the planet within a broader classification scheme, which includes categories like gas giants, rocky planets, and even icy worlds, similar to the planets we are familiar with in our own solar system. Naming exoplanets follows an interesting set of guidelines established by the International Astronomical Union, or IAU. When a new exoplanet is discovered, it is initially assigned a designation based on its parent star's name, often followed by a letter. For example, if a star is named HD 209458, its first discovered planet would be labeled HD 209458b. The letter B indicates it is the first planet found orbiting that star, while the letters continue alphabetically for subsequent discoveries like C or D. Once the scientific community has a consensus on classification, the IAU often invites the public to suggest or vote on names for these planets and their stars. This initiative engages astronomy enthusiasts and allows them to contribute to the astronomical lexicon. The chosen names can reflect mythology, literature, cultural significance, or relate to particular characteristics of the planet itself, adding an extra layer of story and connection to these distant worlds. As a result, the nomenclature and categorization of exoplanets not only serve scientific purposes, but also foster a connection between humanity and the universe. Each name holds the potential for wonder and discovery, sparking the imagination and deepening our understanding of the cosmic tapestry woven with countless planets, many of which may host their own unique stories yet to be uncovered. The naming of an exoplanet goes beyond mere identification. It often reflects cultural, mythological, or scientific significance, inviting a deeper connection between humanity and these distant worlds. Many exoplanets are named after mythological figures, highlighting the rich tapestry of human storytelling. For example, planets like Kepler 22b may possess cultural names that echo the traits and stories of gods and heroes from various cultures. This connection serves to spark our imagination, merging ancient histories with cutting-edge astronomical discoveries. Moreover, the features of these exoplanets sometimes inspire their names. Take the planet HD 209458b, known as Osiris. Named after the Egyptian god of the afterlife, this particular exoplanet features a striking atmosphere that scientists believe could support the study of atmospheric loss. The significance of this name relates not just to mythology, but also to what we can learn about planets with similar characteristics, and by extension, our own understanding of life and habitability beyond Earth. The naming process often involves international collaboration and public input, which can create a sense of global community surrounding these celestial discoveries. Different cultures contribute their own perspectives and interpretations, turning the naming of exoplanets into a celebration of our diverse understanding of the universe. This collective effort underscores our shared curiosity and desire to explore unknown realms, allowing a planet named after a cultural figure to be more than just a dot on a map. It becomes a representation of a collective human aspiration. The names of exoplanets are a bridge between the scientific and the cultural. They allow astronomers, storytellers, and ordinary people alike to engage with the cosmos in a more personal way. As we look to the stars and discover new worlds, the stories we weave through the names we give them enrich our understanding, reminding us of the intricate connection between science, culture, and the narratives that shape our quest for knowledge. The naming of exoplanets, those distant worlds orbiting stars outside our solar system, is increasingly becoming a collaborative effort that includes the public. Organizations like the International Astronomical Union have engaged enthusiasts and everyday people in the naming process, inviting them to submit and vote on names for these fascinating celestial bodies. This initiative does more than just make the names more relatable. It fosters a sense of ownership and excitement among the public regarding astronomical discoveries. When people participate in naming exoplanets, they become emotionally connected to these distant worlds. It transforms an abstract concept into something tangible and understandable. Think about it. Instead of merely reading about planet HD 209458b, which might sound like a complex code, citizens can help name it something meaningful, like nostalgia. Such connections can ignite curiosity about the universe and prompt further exploration into astronomy and science as a whole. Moreover, public involvement in naming exoplanets provides a unique platform for outreach. It encourages educational institutions, libraries, and community organizations to engage in discussions about space and science, sparking interest among young and old alike. When the public feels their choices matter, they are more likely to seek out additional information and share their newfound knowledge with others, creating a ripple effect that can enhance science literacy. Ultimately, by allowing the public to participate in naming exoplanets, we not only enhance engagement with scientific content, but also create a shared narrative about our place in the universe. This collaboration helps demystify science, bridging the gap between experts and enthusiasts, and fostering a more inclusive approach to understanding the cosmos. The names we give these worlds may reflect cultural diversity, history, and imagination, enriching the story of our universe and inviting everyone to join in the exploration. The life cycle of a star is a fascinating and crucial aspect when considering the habitability of its orbiting planets. Stars are born from massive clouds of gas and dust, and their evolution dictates not only their brightness and temperature, but also the environment around them. The life cycle is often divided into stages: the main sequence, red giant, and eventually the end stages like white dwarfs or supernovae. Each of these stages profoundly influences the potential for life on nearby planets. During the main sequence, a star shines steadily, providing a stable energy source. This is the most favorable period for habitability, especially if the planet resides in the star's habitable zone, where conditions allow for liquid water to exist. The duration of this phase can vary greatly. For smaller stars, like red dwarfs, it can last for billions of years, providing a long window for life to potentially develop. In contrast, massive stars burn bright but only for a few million years, an exceedingly short time frame for the emergence of life. As stars evolve into red giants, their outer layers expand and cool, profoundly altering the conditions on nearby planets. This change can lead to intense heating, stripping atmospheres, or rendering planets inhospitable. For instance, if Earth were to orbit the Sun during this phase, it would likely experience catastrophic changes that could make the planet uninhabitable. In the later stages, such as ending as a white dwarf, the diminishing energy output further reduces the chances for life nearby. The life cycle of a star shapes the environment for its planets, influencing the type of climate and potential for life. Understanding these stellar lifetimes and transformations allows astronomers to assess the habitability of exoplanets more accurately, illuminating countless possibilities in the quest for life beyond our own solar system. Each star's journey is unique, offering a varied landscape where life may or may not thrive. Studying dying stars offers us a remarkable window into the future of their exoplanets. When a star reaches the end of its life, it undergoes significant changes, such as expanding into a red giant, which dramatically alters the environment of any planets orbiting it. This transformation can lead to intense heat and radiation that may strip away atmospheres, boil away oceans, or even obliterate the planets altogether. For instance, when our own Sun transitions into a red giant after several billion more years, it will expand beyond its current boundaries. The inner planets, including Earth, will face extreme conditions, potentially rendering them uninhabitable. By observing dying stars in various stages of their evolution, scientists can gather evidence about how different types of stars will evolve and how that will impact their planetary systems. Moreover, the study of dying stars also provides clues about chemical processes. As stars exhaust their nuclear fuel, they eject material into space, enriching the surrounding interstellar medium with heavier elements. These elements can eventually become part of new stars and planets, offering a glimpse into how the composition of exoplanets changes over time. Understanding these cycles gives us insight into the kinds of environments that might shape future worlds. Focusing on older stars allows astronomers to speculate on the fate of nearby exoplanets. By examining the changes happening in dying stars and their influence on surrounding planets, we can draw parallels to similar processes that might be happening in other systems. This rich tapestry of cosmic evolution helps us comprehend not just the life cycles of stars, but also the ultimate destiny of the worlds that dance around them. The lifespan of a star plays a crucial role in shaping the conditions on any orbiting planets, particularly regarding their atmospheres. A star's life cycle can span billions of years, but different types of stars have vastly different lifespans. For instance, a small star like a red dwarf can burn for tens of billions of years, while massive stars might only shine for a few million years before they explode as supernovae. This longevity affects how long a planet can maintain a stable atmosphere, which is essential for supporting life. During a star's main sequence phase, it provides a relatively stable input of energy. This consistency allows a planet's atmosphere to develop and evolve over time. If a planet orbits a star with a long lifespan, like a Sun-like star, there's plenty of time for biochemical processes to unfold, potentially leading to the emergence of life. In contrast, planets orbiting shorter-lived stars might experience environments that change rapidly, hindering the development of complex atmospheres or life as we know it. When a star exhausts its nuclear fuel, it undergoes dramatic transformations that can drastically alter its output of energy. For instance, a star like our Sun will swell into a red giant before shedding its outer layers. Such changes can strip away a planet's atmosphere entirely or radically change its composition. If the atmosphere is lost, it can lead to surface conditions that are inhospitable to life, making the type of star and its lifespan pivotal in determining a planet's long-term habitability. Additionally, the stability of a star's energy output ensures that planets can reach a balance of heat and cold. This balance is essential for maintaining liquid water, a vital ingredient for life. Therefore, when considering the long-term viability of a planet's atmosphere, the lifespan of its parent star is not just an abstract detail. It holds profound implications for the planet's climate, the development of its atmosphere, and the potential for life to thrive. When we explore the vast cosmic ocean of exoplanets, we encounter two key concepts: habitability and the actual presence of life. Habitability refers to the conditions necessary for life to potentially develop, while the presence of life means that some form of living organism has successfully taken root. Understanding the difference between these concepts is essential for speculating about life beyond Earth. The first critical factor of differentiation is the availability of key resources. For a planet to be considered habitable, it typically needs a stable supply of water, a suitable atmosphere rich in essential gases, and the right temperature range that allows for the existence of liquid water. These conditions create a nurturing environment, yet just because a planet meets these criteria does not guarantee life. Life requires more than just resources. It involves complex biological processes that have evolved over time. Another important factor is the planet's geological and climatic stability. Planets that can maintain their environments over geological timescales are more likely to support life. This stability allows for chemical processes to occur, ultimately leading to the formation of life. However, even the most stable environments are not a guarantee that life will emerge. The emergence of life also depends on a multitude of evolutionary advantages and historical contingencies that we may not fully understand. Finally, the interplay between habitability and actual life is influenced by the chemical and physical dynamics at play. For instance, planets that possess the right ingredients may still miss essential catalysts for life to spark. On Earth, for instance, one small but significant factor, such as the presence of lightning or volcanic activity, can catalyze the formation of complex organic molecules. In the universe, the mystery of whether we are alone remains unsolved, as habitability is not just a checklist, it's a delicate dance of conditions that must align perfectly for life to flourish. To understand the potential habitability of exoplanets, scientists use sophisticated laboratory simulations that mimic the extreme conditions found in space. By recreating the atmosphere, pressure, temperature, and even chemical compositions of distant worlds, researchers can study how life, or at least the ingredients for life, might exist under those circumstances. This approach is essential because exoplanets are light years away, and direct observation is limited. In these labs, scientists utilize devices that can replicate the atmospheres of exoplanets by mixing gases under high pressure and varying temperatures. For instance, if an exoplanet has a thick atmosphere rich in carbon dioxide, researchers will create a similar environment, enabling them to investigate how organic molecules behave and whether they can form under those conditions. These experiments help determine the potential for complex chemistry, which is a crucial factor in assessing habitability. Simulations do not occur in isolation. They often involve collaboration across multiple disciplines, including astronomy, chemistry, and biology. As a part of these efforts, researchers study microbial life on Earth that thrives in extreme environments, like deep-sea vents or icy polar regions. Learning how these organisms adapt gives scientists clues about what forms of life could exist on other planets and informs their simulations. Ultimately, these lab simulations provide invaluable insights into the conditions that may foster life elsewhere in the universe. By understanding the limits of life on Earth, scientists can refine their search for habitable worlds, bringing us a step closer to answering the profound question of whether we are alone in the cosmos. The knowledge gained not only enhances our understanding of distant worlds, but also deepens our appreciation for the complexity of life as we know it. The potential discovery of intelligent extraterrestrial life presents humanity with profound ethical dilemmas that touch upon our values, responsibilities, and understanding of our place in the universe. First and foremost, there's the question of how we would interact with such beings. Would we treat them as equals, or would we impose our own views and behaviors upon them? This fundamental issue challenges our ideas about respect and coexistence, pushing us to consider the implications of imposing our beliefs and practices on societies that may be entirely different from our own. There are also concerns regarding communication. How would we convey our intentions to extraterrestrial beings? Would we run the risk of misunderstanding or misinterpretation, leading to conflict rather than collaboration? This dilemma emphasizes the importance of carefully considering our messages, avoiding the use of aggression or superiority. The ability to bridge the communication gap may be crucial in creating peaceful relationships based on mutual understanding and respect. Another significant ethical question involves the potential risks of contact. If we discover intelligent life, what responsibilities do we have to protect both our own planet and theirs? History has shown us that encounters between different cultures on Earth often lead to exploitation and harm. We must ponder whether humanity has the moral capacity to approach such a revelation with caution and responsibility. Every step taken in such an endeavor could have significant repercussions, not just for our species, but for any alien life forms we find. Lastly, we must reflect on how the discovery would impact our own self-identity and worldview. Meeting intelligent extraterrestrial life could challenge religious beliefs, philosophical perspectives, and even the very idea of humanity itself. These reflections compel us to examine our assumptions about life, intelligence, and what it means to be human, suggesting a transformative journey that could ultimately reshape our understanding of existence and our responsibilities within it. This dialogue about the ethical implications of extraterrestrial contact is not just a matter of speculation, but rather a profound inquiry into our character and moral compass as a species. Science fiction has played a pivotal role in shaping public perception and interest in the search for exoplanets. For decades, stories of distant worlds, alien civilizations, and interstellar travel have captured our imagination and prompted us to think beyond our own planet. Films, books, and television series have not only entertained, but have also educated audiences about the possibilities of life beyond Earth. Titles like Star Trek and The Martian have introduced complex ideas about space, planetary systems, and the conditions needed to support life in a way that is accessible and engaging. These narratives often explore themes of exploration and discovery, mirroring the very real scientific endeavors taking place today. As scientists began to discover and catalogue exoplanets, those planets orbiting stars outside our solar system, the public's interest surged. The excitement conveyed in science fiction made the concept of finding Earth-like planets not just a scientific possibility, but an exciting frontier for humanity. From the idea of a Goldilocks zone, where temperatures might be just right for life, to evocative worlds that might hold intelligent beings, these stories have turned abstract scientific concepts into relatable ideas. Moreover, science fiction has inspired actual scientific projects and missions. Books like Contact by Carl Sagan or films such as Interstellar have sparked imaginations and encouraged young minds to pursue careers in astronomy and astrophysics. The wildly popular series The Expanse also delves into the nuances of space travel and the realities of living on other planets, leading to discussions in households worldwide about what exoplanets might be like. Each new discovery in astrophysics tends to evoke a wave of creative storytelling, feeding back into the public's curiosity. As we stand on the cusp of potentially discovering habitable worlds and perhaps even signals from intelligent life, the relationship between science fiction and science, especially concerning exoplanets, becomes even more fascinating. In a sense, these narratives not only reflect our aspirations, but also help steer the conversation towards understanding our place in the cosmos. The shared wonder of these distant worlds, shaped by science fiction, ultimately nourishes both our imaginations and our scientific endeavors. Science fiction has long captured the imagination regarding exoplanets, planets that lie beyond our solar system. One of the most popular scenarios involves humanity establishing colonies on distant worlds. This concept often portrays humans escaping an Earth ravaged by environmental disasters, wars, or overpopulation. In these tales, shining cities arise on planets that mimic Earth's conditions, inviting exploration and settlement where the possibilities seem limitless. Another captivating scenario features intelligent extraterrestrial life. Many stories revolve around the first contact with alien civilizations residing on exoplanets, challenging our understanding of life itself. These narratives often delve into the complexities of communication and cooperation as humanity grapples with the ethical implications of interacting with beings from another world. The rich diversity of imagined alien cultures invites listeners to ponder what life may truly be like, sparking both excitement and trepidation about our place in the cosmos. In addition to colonization and alien contact, stories frequently explore the harsh realities of life on exoplanets. Writers envision worlds with extreme climates and bizarre ecosystems where survival becomes a significant challenge for settlers. These scenarios often serve to highlight humanity's resilience and adaptability, whether depicting thick jungles on gas giants or frozen tundras of icy worlds. Such extreme environments invite reflection on the limits of human ingenuity against the backdrop of breathtaking alien landscapes. Lastly, time travel and alternate realities are common themes involving exoplanets. Some narratives propose exoplanets as gateways to different times or dimensions, leading to thrilling adventures that defy the boundaries of traditional storytelling. In these plots, characters navigate not just the vastness of space, but the very fabric of time and reality itself, allowing for exciting explorations of fate, choice, and consequence. The allure of uncharted worlds and the mysteries they hold continually fuels our fascination with the unknown, encouraging us to dream about what lies beyond the stars. Artistic interpretations of exoplanets often serve as a reflecting pool for our collective hopes and fears as a society. When scientists discover planets beyond our solar system, the artistic community eagerly imagines what those distant worlds might look like. These creative visions are not just whimsical illustrations. They embody our aspirations for the universe, igniting dreams of exploration and the possibility of finding life beyond Earth. For many, these artworks symbolize hope, suggesting that we might one day connect with other intelligent beings or discover new forms of life that could inspire cooperation and understanding. Conversely, the interpretation of exoplanets can also reveal our anxieties about the future. Some artistic representations highlight hostile environments, portraying barren landscapes or climates capable of supporting life but rife with dangers. These visions can reflect societal fears about our own planet's changes due to climate change, resource depletion, or technological advancements. The images remind us of the fragility of life and the potential consequences of our choices, thereby inviting deeper considerations about how we treat our own world. Moreover, these artistic interpretations often delve into the philosophical implications of discovering exoplanets. They ask profound questions about humanity's place in the cosmos. Are we alone in the universe? What would contact with extraterrestrial civilizations mean for our identity and values? Such art can provoke discussions that extend beyond astronomy and delve into ethics, existentialism, and our understanding of consciousness itself. In this way, the art surrounding exoplanets becomes a conduit for exploring what it means to be human. Overall, the artistic exploration of exoplanets serves as a bridge between science and society, linking our empirical understanding of the universe with the complex emotional and philosophical framework within which we navigate life. These creative expressions encourage us to dream while also staying grounded in the realities of our existence, making them a crucial element in the ongoing dialogue about our future among the stars. Kepler 186f stands out in the ever-expanding universe of exoplanets for several compelling reasons. Discovered by NASA's Kepler Space Telescope in 2014, it is notable for its remarkable similarity to Earth, earning it the title of the most Earth-like planet discovered to that date. One of its most striking features is its location within the habitable zone of its star, a region where conditions are just right for liquid water to exist, a crucial ingredient for life as we know it. This exoplanet orbits a star that is a cooler and smaller type, known as a red dwarf. Red dwarfs are abundant in our galaxy, but their faintness means the planets around them experience different conditions compared to those orbiting larger stars like our Sun. Because Kepler 186f receives about 1/3 of the energy that Earth receives from the Sun, its temperatures could permit the presence of liquid water if the planet has a suitable atmosphere. This puts it on the shortlist for potentially harboring life. Furthermore, Kepler 186f is approximately 1.1 times the size of Earth, which places it firmly in the category of a super-Earth. Its slightly larger size suggests it could have a rocky surface. Scientists believe such characteristics make it capable of supporting a climate that could be similar to ours, especially if it has a stable atmosphere. This possibility ignites our imagination about what types of life forms might exist there. The discovery of Kepler 186f opens the door to profound questions about our place in the universe. As we explore these distant worlds, we gain insights into the diversity of planetary systems and the potential for life beyond our own. Each new finding leads us to wonder, just how unique is our Earth in the vast cosmos, and could there be distant cousins of our own planet waiting to be discovered? WASP 121b is a fascinating exoplanet that lies about 800 light-years away from Earth, and it has garnered attention due to its extreme environmental conditions. This particular planet is classified as a hot Jupiter, which means it is a gas giant similar in size to Jupiter, but orbits its star at a blistering close distance. As a result, WASP 121b experiences unimaginably high temperatures, with daytime temperatures soaring above 2,500 degrees Celsius. This is hot enough to vaporize metals, creating a unique and extreme atmosphere. One of the most intriguing aspects of WASP 121b is its distinct weather systems. Unlike Earth, where we think of weather in terms of rain and snow, WASP 121b experiences rain made of molten metals, such as iron and magnesium, due to those extreme temperatures. This scorching weather is driven by the extreme pressure of its atmosphere, which, like a pressure cooker, contributes to the intense climatic conditions. Strong winds sweep across the planet at incredible speeds, leading to highly dynamic and turbulent weather patterns that scientists are excited to study. Additionally, WASP 121b exhibits an unusual day-night temperature contrast. One side, perpetually facing its star, is scorched under relentless sunlight, while the opposite side lies in eternal darkness. This stark division leads to dramatic atmospheric conditions. Scientists suspect that the heat from the daytime side is transferred to the night side, creating some of the fastest winds observed in planetary atmospheres, reaching velocities of up to 2,500 kilometers an hour. Researchers are particularly intrigued by the chemical composition of WASP 121b's atmosphere. Utilizing advanced telescopes to study the fluctuations in light as the planet transits its star, astronomers have detected the presence of various elements, including water vapor and possibly even heavy metals. These insights not only help us understand this alien world, but also contribute to our broader knowledge about the diversity of planetary atmospheres in the universe. Each finding about WASP 121b paints a vivid picture of extremes, inviting us to ponder the mysteries hidden among the stars. The discovery of the exoplanet LHS 1140b has significantly shifted our understanding of potentially habitable worlds. This intriguing planet lies about 43 light-years away in the constellation of the Sculptor. Its size and mass position it nicely within the category of super-Earths, which are rocky planets larger than Earth but smaller than Neptune. What makes LHS 1140b particularly fascinating is its location within the habitable zone of its star, where conditions might be right for liquid water to exist, a crucial factor for life as we know it. What sets LHS 1140b apart from other similar planets is its substantial atmosphere, which scientists believe could harbor the elements necessary for biological processes. Its density suggests it likely has a solid surface, and studies show that it may possess a thick layer of clouds that could regulate temperature variations. This combination of size and atmosphere challenges the traditional notion that only Earth-like planets are suitable for hosting life. In other words, the criteria for habitability are becoming more flexible, suggesting that the universe might be teeming with diverse environments where life could arise. Moreover, the star that LHS 1140b orbits is a red dwarf, which is more stable than many other types of stars. Although these stars can emit radiation that might be harsh on nearby planets, the prolonged cold phase of red dwarfs gives planets like LHS 1140b a longer window for conditions to stabilize and potentially support life. This discovery urges scientists to rethink how they define habitability, recognizing that planets outside our solar system can bring new complexities to the search for extraterrestrial life. Ultimately, LHS 1140b serves as a reminder of the vast possibilities within our galaxy. It encourages researchers to widen their search criteria and consider a more extensive array of planetary environments that might support life. As we continue to study LHS 1140b and similar exoplanets, we are just beginning to scratch the surface of discovering what makes a world potentially habitable, broadening our perspectives and igniting our curiosity about life beyond Earth. International collaborations have become a cornerstone in the study of exoplanets, offering unique advantages that no single country could achieve alone. These partnerships bring together some of the brightest minds in astronomy from around the globe, enabling the sharing of ideas, resources, and technology. By pooling expertise and funding, researchers can take on larger projects that push the boundaries of what we know about planets beyond our solar system. One significant benefit of international teamwork is access to a diverse array of telescopes and observational tools. For instance, while one country may house a powerful ground-based telescope, another may operate a space telescope equipped for different wavelengths. Using these various facilities in unison can enhance data collection, allowing scientists to observe exoplanets from multiple perspectives. This comprehensive approach not only enriches the data, but also helps validate findings, leading to a more reliable understanding of planetary characteristics. Additionally, these collaborative efforts often involve different scientific disciplines, such as chemistry, geology, and atmospheric science. Interdisciplinary teams can analyze exoplanet atmospheres, interpret spectral data, or simulate planetary formation processes, creating a more robust framework for understanding these distant worlds. This integrative approach helps refine our theories regarding how exoplanets form and evolve, as well as their potential habitability. Finally, international collaborations also play a crucial role in fostering a global scientific community. They promote knowledge exchange, encourage innovation, and inspire the next generation of astronomers. Engaging young researchers in collaborative projects cultivates a shared enthusiasm for exoplanet research and leads to new discoveries that excite and expand our understanding of the universe. Ultimately, through cooperation, countries can accelerate the pace of discovery and deepen our understanding of exoplanets, those intriguing worlds that remind us of the vastness of the cosmos. The search for exoplanets, or planets outside our solar system, has become a vibrant area of scientific exploration, with several exciting global projects currently underway. One of the most prominent initiatives is NASA's Transiting Exoplanets Survey satellite, commonly known as TESS. Launched in 2018, TESS is designed to survey nearby stars for transiting planets, observing their dips in brightness as planets pass in front of them. By focusing on bright stars, TESS aims to identify candidate planets that follow-up missions can study in greater detail. Another key player in exoplanet research is the European Space Agency's Plato mission. Set to launch in the coming years, Plato will build on the techniques developed by TESS, aiming to find Earth-like planets orbiting stars similar to our own Sun. With its unprecedented capability to monitor thousands of stars simultaneously, Plato will assist in analyzing light curves that reveal critical information about planetary size, orbit, and potential habitability. Here on Earth, ground-based telescopes are also making significant advancements in exoplanet detection. Projects like the Very Large Telescope in Chile utilize high-precision techniques to directly image exoplanets and gather information about their atmospheres and compositions. Additionally, the Keck Observatory in Hawaii leverages the power of adaptive optics to minimize distortion from the atmosphere, allowing astronomers to measure the light from planets and gain insights into their characteristics. As technology evolves, the future looks promising for exoplanet exploration. Missions like the James Webb Space Telescope, which launched in late 2021, will delve deeper into the atmospheres of these distant worlds, analyzing chemical signatures that might suggest the presence of water, organic molecules, or even signs of life. The collaborative efforts of these global projects highlight humanity's relentless curiosity about the cosmos, ushering in a new era of discovery in our quest to understand the universe and our place within it. The quest to understand exoplanets, or planets orbiting stars beyond our solar system, is a complex and multifaceted endeavor. It draws from diverse scientific disciplines, each adding its unique perspective and expertise. Astronomy plays a leading role by identifying and cataloging exoplanets, using telescopes to detect their light and measure their distances from Earth. Techniques like transit photometry and radial velocity have revolutionized our ability to discover these distant worlds, revealing that many are likely to have conditions suitable for life. However, it's not just astronomers who contribute to this field. Planetary science helps us understand the formation and evolution of these distant planets. By studying our own solar system, scientists can infer processes that may occur around other stars. This comparative approach allows for the enhancement of theoretical models about planetary atmospheres and surface conditions. Insights from planetary geology assist in predicting what materials might exist on exoplanets, which is critical when evaluating their potential habitability. Climate science adds another layer of understanding. By examining how atmospheres behave under various conditions, scientists can simulate what weather and climate might be like on exoplanets with different atmospheric compositions. This is particularly vital for exoplanets within the habitable zone, where temperatures could allow for liquid water to exist. Researchers in this field can share knowledge about greenhouse gases and their effects, shaping our expectations of diverse climates across the universe. Finally, astrobiology ties everything together by asking the fundamental question: could life exist on these planets? By examining extreme environments on Earth, astrobiologists explore the limits of life, strengthening our hypotheses about where life might thrive beyond our planet. The collaboration between these disciplines creates a rich tapestry of knowledge, revealing not only how exoplanets form and evolve, but also how we might one day encounter life far beyond our own solar system. Exoplanets, or planets outside our solar system, have revolutionized our understanding of both planetary formation and the principles governing them. For decades, scientists formulated theories based largely on our own solar system, expecting to find planets that resembled Earth or the gas giants of our system. However, the discovery of exoplanets has revealed a stunning diversity in size, composition, and orbital patterns, raising questions about the mechanisms of planet formation and the processes that govern them. One of the significant surprises has been the existence of gas giants orbiting incredibly close to their stars, a category known as hot Jupiters. Their presence challenges classical planetary formation models, which suggested that gas giants would only form in the cooler outer regions of a solar system. These unexpected findings push scientists to reconsider and refine their theories to account for how such massive planets could form in such extreme conditions. This shift not only enhances our understanding of planetary dynamics, but also reflects on the processes that might be at play in different star systems across the universe. Then, we have the quantum aspects of the materials that make up these worlds. Exoplanet observations have led to the exploration of how quantum mechanics, the branch of physics that describes the behavior of matter and energy at very small scales, affects planetary atmospheres and climates. For instance, The interaction of light with molecules in different planetary atmospheres creates unique spectra. Analyzing these spectra allows scientists to determine the composition of exoplanetary atmospheres, which in turn may offer insights into the fundamental quantum behaviors of materials under various temperature and pressure conditions. Exoplanets are not just curiosities in our night sky, they are vital pieces of a much larger puzzle. They compel scientists to challenge and refine existing theories, revealing that our understanding of quantum mechanics and planetary formation is still growing and evolving. As we continue to discover new exoplanets and deepen our understanding of their environments, we may uncover even more revolutionary insights that reshape our knowledge of the cosmos. The discovery of life on an exoplanet would fundamentally reshape our understanding of consciousness and intelligence. Currently, we tend to view consciousness and the capacity for intelligent thought as phenomena deeply tied to the unique evolutionary paths taken by life on Earth. If life were discovered beyond our planet, it would invite us to reconsider what factors contribute to consciousness. Is it a rare fluke of evolution, or is it a common outcome in the universe, potentially arising under a variety of conditions? Additionally, this discovery could challenge the notion that consciousness is exclusively linked to complex organisms. Imagine a planet populated by simple microbial life, yet those organisms display forms of awareness or responsiveness that hint at primitive forms of consciousness. This raises intriguing questions. What does it mean to be alive or aware? If simpler life forms can exhibit a rudimentary form of intelligence, our understanding of consciousness might need to expand to include a spectrum of awareness rather than a binary distinction between sentient and non-sentient beings. Furthermore, finding intelligent life forms could stimulate profound philosophical inquiries. If an alien civilization has developed its own metrics of intelligence and consciousness, we might see alternative models that differ fundamentally from human experiences. This could lead us to understand consciousness not as a definitive goal of evolution, but rather as a diverse toolkit with varied uses tailored to specific environmental challenges. Ultimately, the implications for theories of consciousness and intelligence extend far beyond scientific curiosity. They may inspire new ways of thinking about our place in the cosmos and prompt a reflection on our definitions of life itself. Exploring the diversity of consciousness across the universe could lead to insights that deepen our appreciation for the unique but interconnected relationship we have with all forms of life. The laws of physics, as we know them, are universal and apply on a grand scale throughout the cosmos, including on exoplanets, which are planets that orbit stars outside our solar system. These laws dictate everything from gravity to electromagnetism, shaping how these distant worlds form, evolve, and behave in their unique environments. For instance, the gravitational pull of a star governs the orbits of its planets, while the interactions of radiation influence atmospheric conditions, temperature, and potential habitability. When scientists discover exoplanets, they study their characteristics by applying the same physical laws observed within our own solar system. The boiling point of water, the force of gravity, and the principles of thermodynamics all come into play. For example, if an exoplanet is too close to its star, it could experience extreme heat, preventing water from remaining in liquid form. Conversely, a planet farther away might be too cold, leading to conditions that are inhospitable to life as we know it. However, the conditions on exoplanets can vary widely, leading to a fascinating array of environments. Some exoplanets orbit in what is termed the habitable zone, where temperatures allow for liquid water, a critical ingredient for life. Others might possess thick atmospheres that create greenhouse effects, trapping heat and potentially supporting a diverse range of chemical reactions. The laws of physics ensure that, regardless of these differences, we can predict certain behaviors based on their environmental conditions. Understanding these principles can help unravel the mysteries of these alien worlds. As astronomers gather data from telescopes and space missions, they employ the laws of physics to interpret the findings, whether it's identifying the atmospheres of strange gas giants or the rocky surfaces of seemingly Earth-like planets. Each discovery is a step towards grasping the complexity and variety of the universe, reminding us of the wonders that lie beyond our own planet. The discovery of exoplanets in multi-planet systems presents intriguing implications for our understanding of the universe. In systems where several planets orbit the same star, researchers can study the interactions and gravitational dynamics between these planets. This helps to shed light on how planets form and evolve over time, offering clues about the processes that may have shaped our own solar system. When we find planets that exist in groups, it suggests a different history of formation than those in solitary orbit. For instance, planets can influence each other's orbits, which may lead to more stable or unstable arrangements over vast periods. This interplay can inform scientists about the likelihood of different types of planetary systems evolving, as well as the potential for habitable zones where conditions might support life. Each new discovery adds pieces to the puzzle of planetary formation and migration theories. Conversely, single-planet systems shift our focus. They provoke questions about why that particular star has no companions, or whether it might form planets later. These solitary planets could also represent unique developmental paths that diversify the types of worlds in our galaxy. Discovering a growing number of single-planet systems invites dialogue about the many environmental factors that contribute to planetary existence. These findings enrich our grasp of planetary ecosystems. Understanding both types of systems provides essential insights into the complexities of formation processes, potentially improving our models of how life-sustaining planets emerge. As more and more systems are studied, we get closer to unraveling the mysteries of our universe and assessing the cosmic neighborhood where life might thrive. The gravitational influence of multiple planets can significantly shape the evolutionary trajectory of their star system. When planets orbit a star, their gravitational pulls interact in complex ways, influencing not only their own orbits but also the orbits of their neighbors. This interconnected gravitational dance can lead to changes in orbital shapes, distances, and even stability over millions of years. For instance, when a large planet like Jupiter moves around its star, its substantial mass can affect the orbits of smaller planets nearby. It can stabilize some orbits and destabilize others, possibly leading to collisions or ejections of smaller bodies. This interactive gravitational field not only dictates the fate of planets, but also influences the distribution and trajectory of smaller celestial objects, such as asteroids and comets. Moreover, these gravitational interactions can affect the star itself. They can influence the rotation of the star and its magnetic activity, which in turn can have profound effects on the habitable zones of the system. Changes in the star's magnetic field and solar output can greatly affect potential life-supporting conditions on planets within the system. The gravitational interplay among multiple planets plays a crucial role in both the stability and evolution of the star system as a whole. These dynamics can lead to the emergence of habitable environments or, conversely, conditions that may inhibit the development of life, ultimately shaping the story of that planetary system through the ages. Exoplanets, or planets beyond our solar system, exhibit an extraordinary variety of orbits and alignments, which reveal much about their formation and the dynamics of their systems. One of the most compelling features observed is the diversity in orbital shapes. While our Earth follows a nearly circular orbit, many exoplanets have highly elliptical trajectories, which can lead them to swing dramatically closer to their stars at certain points in their orbits. This suggests that exoplanets often experience gravitational interactions with other planets, causing their paths to shift over time. Another fascinating aspect of these orbits is their alignment relative to their host stars. In some systems, exoplanets orbit in a plane that is closely aligned with the star's own equatorial plane. This could indicate a relatively peaceful formation history, where the protoplanetary disk around the star was stable and uniform. However, astronomers have discovered systems where planets have orbits that are tilted at significant angles to this stellar plane, pointing to more tumultuous past interactions, possibly involving close encounters with other bodies or more complex migration patterns. What do these alignments and orbital shapes imply about the origins of these planetary systems? They suggest that the processes of planet formation are far more chaotic than once believed. Depending on factors such as the mass of the star, the presence of other planets, and even the gravitational influence of nearby stars, each system develops its unique configuration. For instance, a crowded environment with many large planets can lead to more eccentric orbits, potentially revealing vital clues about the influences at play during the early stages of the system's development. The observed variety of orbits and alignments in exoplanetary systems is a window into understanding not just the nature of those individual planets, but also the broader mechanics of astrophysics. By studying these characteristics, scientists can uncover hints about planet formation, the evolutionary pathways of planetary systems, and even the potential for habitability within these diverse worlds. The journey of planetary science has undergone remarkable transformations since the groundbreaking discovery of the first exoplanet in the early 1990s. Back then, astronomers identified a planet orbiting a distant star, marking a pivotal moment in our understanding of the cosmos. This historic observation opened the floodgates to a new realm of exploration, igniting our curiosity about planets beyond our own solar system. As technology advanced, so did our methods of detection. Initially reliant on techniques like the radial velocity method, which measured the gravitational influence of a planet on its star, scientists soon embraced a variety of innovative approaches. The transit method, which detects the dimming of a star's light as a planet passes in front of it, has become particularly fruitful. Telescopes like Kepler and more recently TESS have expanded our catalogue of known exoplanets dramatically, leading to the discovery of thousands of these distant worlds. Our understanding has also evolved in terms of the types of planets we find. We started with a focus on large gas giants mirroring our own Jupiter and Saturn, but we now recognize an incredible diversity of planetary types. From hot Jupiters, which orbit very close to their stars, to Earth-sized rocky planets in habitable zones, the variations are staggering. This diversity invites deeper questions about how planets form and evolve, and whether conditions might exist elsewhere that could support life. Moreover, the study of planetary atmospheres has taken center stage as we learn more about the chemical compositions of these distant worlds. By examining the light that filters through a planet's atmosphere during transits, scientists can identify which gases are present. This not only tells us about the planet's climate and potential habitability, but also provides insights into the processes shaping planetary systems. As we continue to explore and learn, our understanding of planetary science is transforming, revealing a richer and more complex universe than we ever imagined. The quest to understand worlds beyond our own has deep roots in the history of astronomy. Among the key figures who laid the groundwork for exoplanet research is the renowned Italian scientist Galileo Galilei. His pioneering observations in the early 17th century, made with one of the first telescopes, fundamentally changed how we perceive the universe. Galileo's studies of celestial bodies in our solar system prompted future generations to wonder about planets orbiting other stars. Fast forward to the late 20th century, and we find the astrophysicist Frank Drake at the forefront of exoplanet discussions. In 1960, Drake established the Drake equation, a formula intended to estimate the number of communicating civilizations in our galaxy. While primarily focused on extraterrestrial life, this framework highlighted the importance of knowing about other planetary systems, triggering an uptick in interest and research into planets beyond our solar system. Another pivotal figure is Michel Mayor, a Swiss astronomer who, along with his colleague Didier Queloz, made history in 1995. They became the first to confirm the existence of an exoplanet orbiting a Sun-like star, a giant planet named 51 Pegasi b. Their discovery not only revolutionized our understanding of planetary systems, but opened the floodgates for thousands of exoplanet discoveries that followed, dramatically shifting the field of astronomy. Lastly, we must mention the role of space telescopes, particularly the Hubble Space Telescope and the Kepler Space Telescope, which launched in 2009. Kepler's mission was specifically designed to find new exoplanets, transforming our ability to discover and study them. The insights gained from these astronomical endeavors have significantly enriched our understanding of the universe and our place within it, inspiring an ongoing exploration of the stars and the potential for life beyond Earth. Past scientific misconceptions about planets have considerably shaped the ways contemporary researchers approach their studies. These misunderstandings often stem from early observations made with limited technology, leading scientists of the past to draw conclusions that we now recognize as flawed. For instance, Many believed that the planets moved in perfect circles and that the Earth was at the center of the universe, a view that was dominant until the observations of Copernicus and Galileo began to shift our perspective. These historical errors remind today's scientists of the importance of questioning established beliefs and remaining open to new evidence. The journey from a geocentric to a heliocentric model marks a pivotal turn in our understanding of the solar system. This evolution encourages a cautious optimism in modern research, pushing scientists to design experiments and observations that rigorously test hypotheses to avoid repeating the mistakes of the past. The recognition of past errors reinforces the practice of skepticism, leading today's planetary researchers to validate their findings through repeatable experiments and peer-reviewed work. Moreover, these misconceptions influence technological advancements and research methodologies. For example, once we understood that planets do not follow perfect circular orbits, it prompted the development of more sophisticated models and simulation software. Researchers now use complex algorithms and powerful telescopes, such as the James Webb Space Telescope, to explore the cosmos with precision unrivaled in earlier times. Each correction of past misunderstandings has allowed researchers to fine-tune their approaches, factoring in variables like atmospheric conditions and gravitational influences that were previously overlooked. Finally, education plays a significant role. The narrative of how our understanding has evolved is essential in teaching future generations of scientists. Incorporating the history of misconceptions into curricula not only provides context, but also instills an appreciation for the scientific method. We learn that science is a journey of revisions and adaptations, encouraging an ongoing quest for knowledge and ensuring that modern research methodologies remain ever more resilient against the allure of oversimplified conclusions. Through understanding our past, we empower our future explorations of the planets and beyond. The discovery of advanced civilizations on exoplanets carries profound implications for our own future. One significant aspect is the possibility of collaboration and knowledge exchange. If we find civilizations that have mastered technologies far beyond our current capabilities, we might have the opportunity to learn from their advancements. This knowledge could help us solve pressing issues like climate change, resource scarcity, and health crises, enabling humanity to evolve more rapidly in areas we currently struggle with. Moreover, the existence of intelligent life elsewhere prompts us to reflect on our own trajectory as a civilization. We could begin to understand the lifespan and sustainability of civilizations by studying their development. If advanced civilizations have thrived for thousands or even millions of years, this might inspire us to consider how we can extend our own existence without collapsing under the weight of our technological advancements and societal challenges. The study of their histories could offer us vital lessons on resilience, cooperation, and ethical governance. Conversely, the scenario of advanced civilizations introduces a note of caution. The potential for conflict or misunderstanding remains high, especially if such civilizations view us as a lesser species or if we misinterpret their intentions. It may also remind us that technological advancement does not always equate to moral progress. Understanding this dynamic could reshape international conversations about technology, surveillance, and our own responsibilities as stewards of Earth. Ultimately, contemplating the implications of advanced civilizations compels us to look inward. We are challenged to examine our own values and behaviors. This exploration could reinforce the necessity for global cooperation and unity as we face the vastness of the cosmos. Knowing we are not isolated can inspire a greater sense of purpose, urging us to become better custodians of our own planet and potentially a more enlightened part of a broader cosmic community. Transhumanism is a philosophical movement that advocates for the enhancement of the human condition through advanced technologies. At its core, transhumanism explores the potential for humans to evolve beyond their current physical and mental limitations. This concept becomes particularly relevant when we consider the exploration of exoplanets and the quest for humanity's long-term survival beyond Earth. As Earth faces numerous challenges, including climate change, resource depletion, and potential existential threats like asteroid impacts, the idea of colonizing exoplanets emerges as a viable solution. In this pursuit, transhumanists envision a future where human beings are equipped with enhanced capabilities, such as advanced physical traits, improved cognitive functions, or even biotechnological adaptations that make it possible to thrive in alien environments. This futurist perspective encourages the development of technologies that could allow humans to withstand harsher conditions on distant worlds, such as reduced gravity or extreme temperatures. Furthermore, exploring exoplanets offers a unique opportunity for transhumanism to intersect with space exploration. As we search for habitable worlds, humans may need to rethink what it means to be human. If colonization becomes essential, our understanding of human biology might need to evolve. Transhumanists advocate for creating hybrid beings, combining human biology with artificial intelligence or enhancing our natural abilities through genetic engineering. This could enable us to adapt to various environments that current humans cannot survive in. The pursuit of exoplanets for humanity's survival is inherently linked to transhumanist ideals. As we expand our horizons and look to the stars, the idea of enhancing human capabilities becomes crucial. By merging technology with our biological essence, we may not only find new homes beyond Earth, but also redefine what it means to be truly human in a universe filled with possibilities. As we gaze into the vastness of the cosmos, the prospect of studying distant exoplanets sparks the imagination. Emerging technologies are paving the way for profound advancements in our understanding of these distant worlds. One such innovation lies in the field of space telescopes. Instruments like the James Webb Space Telescope are designed to peer deeper into the universe than ever before. With their remarkable capabilities to detect faint signals from far-off planets, these telescopes can analyze light that passes through a planet's atmosphere, uncovering the chemical signatures of substances like water, methane, and oxygen, key ingredients for potential life. Another exciting frontier in exoplanet exploration is the development of advanced robotic space missions. Concepts like the Interstellar Probe aim to travel beyond our solar system to gather data from neighboring star systems. These robotic explorers could utilize cutting-edge propulsion systems, such as solar sails or ion drives, allowing them to cover vast distances much faster than conventional spacecraft. By sending these probes equipped with sophisticated instruments, we could gain direct insights into the atmospheres and surface conditions of exoplanets, which would dramatically enhance our understanding of their potential habitability. Artificial intelligence is also playing a crucial role in this evolving landscape. AI can sift through massive amounts of astronomical data far quicker than human researchers. By using machine learning algorithms, scientists can recognize patterns and anomalies in light curves that might indicate the presence of exoplanets or even signs of biological activity. This capability not only speeds up the discovery process, but also assists in the analysis of already known exoplanets, providing fresh perspectives on their environments. Furthermore, the concept of space elevators has emerged as another potential game changer for exploration. A space elevator would consist of a cable tethered to a base on Earth, stretching into space. This structure could facilitate easier access to orbit, allowing for the deployment of more sophisticated instruments for studying exoplanets. While still in the realm of theoretical engineering, such a technology could revolutionize how we launch missions, making space travel more efficient and economically viable. As these technologies continue to develop, the dream of understanding distant worlds draws ever closer, turning science fiction into potential reality. Educating the public about exoplanets, those intriguing worlds beyond our solar system, requires a blend of engaging strategies. One of the most effective methods is storytelling. When scientists share their discoveries about exoplanets through narratives, it captures the imagination. By framing complex data within relatable stories, like the journey of a planet similar to Earth, audiences can connect more deeply with the information. Interactive platforms play a crucial role too. Science centers and planetariums can use immersive experiences like virtual reality and augmented reality. These technologies allow people to explore distant worlds and experience conditions on exoplanets firsthand, making the concept not just theoretical but almost tangible. Such experiences not only inform but also inspire awe, prompting further interest and inquiry. Utilizing social media is another powerful strategy. Scientists and educators can share captivating images and updates about their research in bite-sized formats. Through platforms like Twitter or Instagram, engaging visuals of exoplanet atmospheres, or illustrative comparisons with our solar system can reach diverse audiences. This approach democratizes information, bridging gaps between academia and everyday life in a manner that is both accessible and compelling. Lastly, collaborating with educators to incorporate exoplanet science into school curricula is vital. By integrating lessons on space exploration and the search for extraterrestrial life in classrooms, we can foster curiosity from an early age. This foundational knowledge builds a generation more aware of our place in the universe and the significance of ongoing discoveries in the field of astronomy. Through these approaches, we can cultivate a well-informed public eager to understand the cosmos and our potential neighbors among the stars. Social media has become a powerful tool for generating excitement and awareness about scientific discoveries, including the fascinating realm of exoplanets. As we venture beyond our solar system, the ability to share findings instantly with a global audience plays a crucial role in engaging the public. Through platforms like Twitter, Instagram, and Facebook, scientists can share updates, stunning visuals, and real-time data about exoplanets, capturing the imagination of millions. One of the most effective ways to harness social media is by using compelling imagery and interactive content. For example, images of distant worlds taken by telescopes can be beautifully presented alongside engaging infographics that explain the significance of these discoveries. By inviting the audience to explore virtual simulations of exoplanets or even participate in discussions and Q&A sessions, scientists can create a captivating dialogue that draws people in. This deeper engagement not only informs but inspires curiosity about the universe. Moreover, collaborating with influencers and creators who specialize in science communication can broaden the reach of exoplanet discoveries. When popular science communicators or educators share their excitement and insights about new exoplanet findings, they can reach audiences that traditional scientific papers might not. This helps bridge the gap between scientific communities and the general public, fostering a shared wonder about the universe beyond our own. Lastly, campaigns focused on special events, such as significant discoveries or anniversaries of landmark missions, can generate collective excitement. Hashtags, live streams, and countdowns can engage audiences and create a sense of community around these celestial revelations. By keeping the conversation alive and encouraging participation, social media can turn what might seem like distant discoveries into a shared journey of exploration, sparking enthusiasm for astronomy and understanding of our place in the cosmos. Educational institutions play a vital role in nurturing the next generation of astronomers and exoplanet researchers. They offer the foundational knowledge and skills that students need to explore the vastness of space. In schools and universities, students are introduced to core subjects like physics, mathematics, and computer science, which are essential for understanding the complexities of celestial bodies and their movements. By providing a structured environment for learning, these institutions spark curiosity and inspire students to consider careers in astronomy and related fields. Moreover, educational institutions serve as hubs for research and discovery. Many universities host observatories and research facilities that allow students and faculty to conduct hands-on experiments and observations. This practical exposure is crucial for developing skills in data analysis, telescope operation, and research methodologies. These environments foster collaboration among students and faculty, often leading to innovative discoveries that can make significant contributions to our understanding of exoplanets and other celestial phenomena. Mentorship is another critical aspect of the role that educational institutions play. Professors and researchers guide students, igniting their passion for space exploration while providing crucial insights and career advice. This mentorship can shape students' future paths, helping them navigate the complexities of academic and research opportunities. Networking within these institutions often leads to collaborations between students and professionals in the field, enhancing their learning experiences and placing them on a trajectory towards successful careers. Finally, educational institutions are pivotal in making astronomy accessible to a broader audience. Through outreach programs, public lectures, and workshops, they engage the community in conversations about space exploration and scientific discovery. By introducing young people to the wonders of the universe, Educational institutions not only build the workforce of tomorrow, but also foster a culture of curiosity and appreciation for science, ensuring a continued interest in astronomy for generations to come. The study of exoplanets, those planets orbiting stars outside our solar system, has dramatically changed our understanding of where life could exist beyond Earth. For a long time, scientists reasoned that if we found other planets, they might share characteristics with Earth, making them candidates for hosting life. With advancements in technology, astronomers have discovered thousands of such worlds, broadening our perspectives significantly. This growing catalogue of exoplanets reveals an extraordinary diversity, leading us to contemplate the various conditions under which life might flourish. Many of these exoplanets orbit in what scientists call the habitable zone. This area around a star is where temperatures could allow liquid water to exist, essential for life as we know it. However, the quest for life shouldn't just hinge on finding Earth-like planets in this zone. The discovery of extremophiles, which are organisms thriving in Earth's harshest conditions, suggests that life could potentially emerge in environments vastly different from our own. This insight inspires scientists to consider a wider range of habitable conditions, including those on gas giants or icy moons, which may house subsurface oceans. The methods of studying these distant planets also enrich our understanding of atmospheres and potential biosignatures or indicators of life. By examining the light that filters through an exoplanet's atmosphere as it passes in front of its host star, researchers can discern components like oxygen or methane. The presence of these gases could point to biological processes and offers exciting possibilities for identifying signs of life in our galaxy and beyond. Ultimately, the exploration of exoplanets not only highlights the potential for life across the universe, but also invites profound questions about our own existence. As we peer into the cosmos, we are reminded that life may be commonplace, waiting for us to discover it. The continuous journey of understanding these distant worlds reignites the age-old question: are we alone in this vast universe, or are there many forms of life just waiting to be found? The answers to these queries lie among the stars, encouraging us to keep looking up. As we gaze into the cosmos, the hunt for exoplanets has revealed a stunning diversity of worlds beyond our solar system. By comparing the chemical processes that occur on these distant planets, scientists can uncover a wealth of information about their atmospheres, potential for life, and even their geological activities. This comparative analysis offers insights into how each exoplanet's unique conditions shape its chemical landscape. Each exoplanet presents its own set of environmental variables, such as temperature, pressure, and chemical composition. For example, an exoplanet that orbits close to its star may experience extreme heat, leading to the formation of different chemical compounds in its atmosphere compared to a colder, more distant planet. Analyzing these differences helps scientists understand how various factors contribute to atmospheric phenomena like cloud formation, weather patterns, and even the likelihood of hosting life. Moreover, studying volatile elements and molecules, such as water vapor, carbon dioxide, or methane, can reveal important clues about an exoplanet's history. For instance, the presence of a particular gas might suggest geological activity, such as volcanic eruptions that release gases trapped in the planet's crust. Alternatively, the absence of expected compounds could indicate harsh conditions that prevent complex chemistry from occurring, steering our search for life towards more promising candidates. By piecing together the chemical puzzle of exoplanets, researchers can refine their models of planetary formation and evolution. It's a fascinating discovery process, where each new data point not only enhances our understanding of these distant worlds, but also reflects the diverse possibilities within our own universe. The comparative analysis of exoplanets, therefore, is not just an academic exercise. It's a journey into the intricate dynamics of chemistry that shapes the very fabric of the cosmos. Exoplanets, or planets located outside our solar system, play a surprisingly significant role in our understanding of dark matter and the broader cosmos. By studying these distant worlds, scientists can gather critical information not only about planetary formation and potential habitability, but also about how celestial bodies interact with their environment. This includes their gravitational effects, which can give us insights into the unseen mass in our universe, dark matter. When an exoplanet transits its star, causing a slight dimming of the star's light, astronomers meticulously measure this phenomenon. Analyzing the light curve, the graph of brightness over time, allows researchers to infer the planet's size, orbit, and mass. This data can then be used to understand the star's mass more accurately, which in turn can extend to the galactic implications of dark matter distribution. The way these exoplanets maneuver within their star's gravitational fields informs us about the mass present in that section of space, some of which could be dark matter. Moreover, peculiarities in the motion of exoplanets can act as fingerprints of dark matter. If dark matter exists in clumps throughout the universe, some of these clumps can exert gravitational forces that subtly influence the orbits of nearby celestial bodies. By observing these gravitational interactions, astronomers can infer the presence of dark matter, piecing together its distribution and density across the cosmos. Ultimately, measuring the subtle effects that exoplanets have on their parent stars expands our understanding of the universe and strengthens our knowledge of dark matter. As we detect more and more exoplanets with advanced telescopes and techniques, we gradually unlock the mysteries of both these distant worlds and the elusive dark matter that shapes our universe. Each discovery adds to a larger tapestry of cosmic understanding, drawing us closer to answers about the most profound questions we have about the fabric of reality. The potential discovery of life on exoplanets raises profound existential questions that touch on the very essence of our humanity. One of the most pressing inquiries involves our place in the universe. Are we alone, or is there a vast community of life forms scattered among distant stars? The realization that life exists elsewhere could fundamentally alter our understanding of life itself and what it means to be human. Additionally, the existence of extraterrestrial life forces us to reconsider the nature of intelligence. If we find life, how similar or different might it be from us? Would these beings possess consciousness, culture, or even technology? This leads us to reflect on the diversity of life's forms and the shared experiences that might connect us across the cosmos. It provokes questions about communication, understanding, and the possibility of relationships with entirely different forms of intelligence. Then, there are implications for our own existence and survival. The exploration of life beyond Earth prompts us to ask whether we are a rarity or simply one of countless life forms thriving throughout the universe. It may prompt us to consider life's resilience and adaptability, challenging our assumptions about survival in various environments, including those that might be extreme or inhospitable by Earth standards. Lastly, the discovery of life on exoplanets could invoke philosophical inquiries about ethics and responsibility. If intelligent life is found, how should we engage with it? Would we continue our explorations and attempts at contact? The realization that we share the universe with other sentient beings positions humanity within a larger ethical framework, one that could guide how we relate to one another, to other life forms, and to our own planet as stewards of all life in this vast cosmos. Philosophical perspectives play a significant role in shaping how scientists explore and interpret the findings concerning exoplanets. At the heart of scientific inquiry lies a fundamental question: what is the nature of reality? Different philosophical outlooks can lead to varying interpretations of data gathered from telescopes, space probes, and other research methods used to study planets beyond our solar system. For example, a materialist viewpoint might emphasize measurable physical phenomena while downplaying any abstract implications of findings. In contrast, a more idealist philosophy might inspire researchers to explore the potential for life or consciousness beyond Earth. This can shift the focus of research questions, from merely identifying exoplanets to investigating the conditions for life or the potential for technology to detect signals from intelligent civilizations. Another critical philosophical influence stems from our understanding of what constitutes evidence and knowledge. Epistemology, the study of knowledge, guides scientists in interpreting the data they collect. If one subscribes to a more empirical philosophy, they may favor direct observational data and reproducibility as the cornerstones of scientific progress. Others might argue that theoretical frameworks, shaped by philosophical concepts, are necessary to guide the interpretation of sparse or indirect evidence, such as that provided by transit methods or spectrographic analysis. Overall, the interplay between philosophy and science fosters a deeper inquiry into exoplanets, encouraging us to question our assumptions. The way we conceptualize life, existence, and even our own place in the universe influences the questions we ask and the significance we assign to discoveries. With each new exoplanet study, we edge closer to a broader understanding of our universe, a quest that marries the empirical rigor of science with the rich tapestry of philosophical thought. The discovery of exoplanets, those planets orbiting stars outside our solar system, has significantly transformed the way we understand our place in the universe. Traditionally, Anthropocentrism, the belief that human beings are the central or most significant entities, shaped how we viewed our environment and the cosmos. Earth was seen as the pinnacle of creation, a unique bastion of life. However, as we began to uncover thousands of exoplanets, many of which exist in habitable zones, we started to realize that Earth is just one of countless worlds, possibly brimming with life and diverse ecosystems. This realization invites us to reconsider our significance in the grand scale of the universe. The sheer variety of environments found on these distant worlds, some resembling Earth closely while others flaunt extreme conditions, challenges the notion that life must be similar to what we know. The potential for life to manifest in forms and ways we had never imagined encourages humility in our assumptions and a recognition of our own limitations. Rather than being the focus of the universe, humans may merely be one possible outcome of the cosmic conditions at play. Moreover, the concept of anthropocentrism intertwines with ethical considerations regarding our treatment of the Earth and other forms of life. If we accept that life can potentially flourish in many forms across the universe, it encourages us to respect and preserve the diversity of life here on Earth. It suggests that the universe can generate life independently of human civilization, prompting a dialogue about stewardship and our responsibility to protect this planet. A broader understanding of life can foster deeper appreciation for the rich tapestry of ecosystems, presenting us as custodians rather than rulers. As we continue to discover new exoplanets, each one becomes a reminder of the vastness of the cosmos and the myriad possibilities it holds. Each distant world challenges us to think beyond the limits of our own experience. In doing so, we can foster a sense of connectedness with the universe at large, embracing a perspective that values all forms of existence rather than positioning ourselves at the center of the universe's narrative. This shift invites us into a richer relationship with the cosmos, which holds more mysteries than we can yet comprehend. Throughout history, the concept of life beyond Earth has been met with a rich tapestry of interpretations across various cultures. In some ancient societies, the stars were seen as the dwelling places of divine beings or ancestors, influencing their beliefs about the cosmos. For example, in many indigenous cultures, celestial bodies are often linked to creation stories, and life beyond Earth is intrinsically woven into their spiritual frameworks. These perspectives can foster a sense of connection to the universe, prompting questions about humanity's place within it. Conversely, many Western cultures, particularly during the Enlightenment, began to approach the cosmos through a scientific lens. The idea of extraterrestrial life shifted from myth to an inquiry grounded in observation and reason. Notably, the works of philosophers and scientists like Giordano Bruno and Carl Sagan invited people to consider the universe as a vast expanse potentially brimming with life. This historical shift not only ignited scientific curiosity, but also propelled advancements in technology and exploration, leading to missions aimed at discovering signs of life beyond our planet. Cultural beliefs also directly impact the way scientific inquiry is conducted. For instance, societies that view Earth as unique may prioritize finding life on Mars or within our solar system. In contrast, cultures that embrace the notion of life existing elsewhere without restrictions may support broader searches for exoplanets capable of supporting life. These differing perspectives can shape funding for research and the types of experiments scientists undertake, as well as influence public interest in space exploration. Ultimately, as diverse cultures continue to share their interpretations of life in the universe, they enrich the scientific discourse. The collaborative interactions between cultural beliefs and scientific exploration enhance our collective quest to understand not just our place in the cosmos, but the possibilities of other life forms existing among the stars. This ongoing dialogue between humanity's cultural narratives and scientific endeavors keeps the curiosity alive, inviting each generation to reflect on what it means to be human in a universe that may not be as empty as we once thought. International cooperation in exoplanet research opens the door to a wealth of exciting possibilities and advances in our understanding of planets beyond our solar system. By pooling resources, knowledge, and expertise from various countries, scientists can undertake more ambitious projects that no single nation could manage alone. This collaboration helps to share the financial burden while allowing researchers access to advanced technologies and instrumentation that enhance our capacity to detect and analyze distant worlds. Moreover, teamwork across borders fosters a diversity of ideas and perspectives. Different approaches in science can lead to innovative techniques for discovering and studying exoplanets. For instance, a satellite designed in one country could work synergistically with ground-based telescopes in another, leading to more comprehensive observations. This kind of collaboration not only accelerates progress, but also enriches the scientific dialogue, allowing researchers to learn from each other's experiences and methodologies. Additionally, sharing data on exoplanet discoveries creates a more thorough and robust understanding of these celestial bodies. When scientists from different countries contribute to a common database, they enable a richer analysis and a higher chance of significant breakthroughs. This inclusive approach leads to improved understanding of potential planetary habitability and the myriad factors that contribute to a planet's atmosphere and conditions. Finally, international cooperation can inspire public interest and investment in science. Collaborative missions project a united front, which can capture the imaginations of people worldwide while promoting education and engagement in the sciences. When researchers from various nations unveil findings together, it showcases a collective human effort to explore the universe, fostering a sense of shared purpose that benefits all of humanity. This journey beyond our planet is not just an exploration of the cosmos, but a testament to what we can achieve when we work together. The study of exoplanets, those distant worlds orbiting stars beyond our own solar system, opens fascinating windows into the dynamics of planetary bodies, including our Earth. By examining the various atmospheres, geological features, and potential climates of these exoplanets, scientists can glean critical insights into the processes that shape all planets, including our own. This comparative approach allows for a deeper understanding of the Earth's unique characteristics and the challenges we face today. For instance, by studying exoplanets that exhibit extreme greenhouse effects, researchers can better grasp the impacts of climate change on Earth. Some exoplanets have thick atmospheres that trap heat, creating uninhabitable conditions. Observing these worlds lends perspective to our own atmosphere's delicate balance and highlights the importance of greenhouse gas concentrations and their long-term effects on climate. In turn, this knowledge can inform our responses to global warming and ecological challenges here at home. Moreover, the geological activities of other planets provide a broader context for understanding Earth's tectonic processes. Many exoplanets exhibit volcanic activity or unique surface formations that serve as analogues to Earth's geology. Studying these phenomena helps scientists unravel mysteries about plate tectonics, the formation of mountains, and the evolution of planetary surfaces. This cross-comparison can help sharpen our focus on natural disasters such as earthquakes and volcanic eruptions, making Earth's processes clearer in the grander cosmic picture. In addition, the search for life beyond our planet hinges on understanding conditions that might foster habitability. By examining which exoplanets lie in the so-called Goldilocks zone, where conditions are just right for liquid water, scientists enhance their comprehension of what makes Earth a unique oasis in the vastness of space. This quest not only enriches our knowledge of planetary formation and evolution, but also guides efforts in protecting and preserving our own planet's delicate ecosystems amidst growing environmental pressures. As we venture deeper into the study of exoplanets, several captivating themes and discoveries are poised to shape our understanding of the cosmos. Firstly, the search for potentially habitable worlds is at the forefront of exoplanet research. Scientists are not merely cataloguing newly discovered planets, but are delving into their atmospheres and chemical compositions to seek out the conditions that might support life. Instruments like the James Webb Space Telescope will play a crucial role in this effort, allowing us to analyze the atmospheres of these distant worlds for signs of water vapor, methane, and other vital indicators. Another significant theme emerging from exoplanet research is the diversity of planetary systems. Our solar system, with its relatively uniform arrangement of rocky and gas planets, is just one of many possibilities. Astronomers have discovered systems featuring not only gas giants orbiting close to their stars, but also unlikely arrangements such as super-Earths and mini-Neptunes. Each discovery adds to a growing catalogue of the variety of planets and orbits that exist throughout the universe, prompting scientists to rethink the dynamics of planet formation and migration. As technology continues to advance, researchers will also explore the atmospheres of exoplanets in unprecedented detail. Future missions aim to identify chemical biosignatures, which are indicators that life, as we know it, might exist or have existed on these planets. The ability to detect complex organic molecules and analyze light spectra from distant worlds may provide insights into evolutionary processes and the potential for alternative life forms. Lastly, the exploration of exoplanets invites us to confront profound philosophical questions about our place in the universe. As we uncover more about these distant worlds, we grapple with the implications of finding life beyond Earth. The realization that we might not be alone could reshape our understanding of life itself, pushing us to expand our definitions of habitability and intelligence. Each discovery not only adds a new chapter to our scientific knowledge, but also deepens our connection to the universe, reminding us of the wonders that lie beyond our home planet. The documentary format serves as a powerful tool in enhancing public understanding and appreciation of the complexities of exoplanets. By blending stunning visuals with engaging narratives, documentaries can bring to life the vast and mysterious worlds that exist beyond our own solar system. This visual storytelling captures the imagination, allowing audiences to see what exoplanets might look like, how they are discovered, and the various conditions that make them unique. When viewers can visualize distant planets and their potential for habitability, it ignites a sense of wonder about the universe. Moreover, documentaries can simplify complex concepts related to exoplanets through expert interviews and accessible explanations. Speaking directly to scientists and astronomers, filmmakers can distill the intricacies of astrophysics and planetary science into relatable language. By breaking down technical processes like the transit method or radial velocity, audiences can grasp how scientists determine the presence of exoplanets and assess their characteristics. This approach not only informs, but also demonstrates the collaborative effort within the scientific community, bringing researchers' enthusiasm for discovery directly into people's living rooms. The pacing of a documentary allows for a deeper exploration of themes, encouraging viewers to ponder larger questions about life in the universe. By interweaving narratives of new discoveries with the historical context of our understanding of planets, filmmakers can emphasize our journey as explorers of space. This approach fosters a sense of connection, as audiences reflect not just on what exoplanets are, but also on what they represent, a beckoning call from the cosmos, inviting us to continue our quest for knowledge beyond the stars. Finally, the emotional resonance of documentaries can create a lasting impact. By telling stories of the search for exoplanets and the quest to find Earth-like conditions, filmmakers can evoke feelings of curiosity, hope, and awe. This emotional engagement is vital. It encourages viewers to appreciate not only the science, but the broader implications for humanity. By nurturing a sense of shared curiosity and responsibility for our place in the universe, documentaries can stimulate public interest in both astronomy and the critical nature of the scientific inquiry that continues to explore the cosmos.